Think about how a computer recognizes a face, spots a fraudulent credit card transaction, or understands human speech. If you strip away all the software libraries and complex tools, the core mechanism is surprisingly simple. Basic math operations working together in harmony. Every major leap in artificial intelligence comes back to one simple building block: a single artificial neuron that learns how to separate right answers from wrong ones. To truly understand how neural networks work under the hood, we need to start at the very beginning by exploring how a single neuron takes in signals, weighs its options, and makes a decision. Visualize a single artificial neuron as an analytical processing node positioned at a junction between incoming data streams and an outgoing decision channel. Data weights act as amplification or attenuation dials on each incoming signal. A large positive weight indicates that the corresponding feature provides strong positive evidence toward a particular decision. A weight near zero indicates that the feature is largely irrelevant to the outcome. A negative weight signifies that higher values of that feature penalize or decrease the probability of a positive decision. In our financial evaluation analogy, the credit score feature would receive a high positive weight, while the total existing debt feature would receive a negative weight, reflecting the risk associated with existing liabilities. As incoming numerical features travel down their respective pathways, the neuron multiplies each feature value by its assigned weight. The neuron then gathers all these individual weighted values into its central processing body and sums them together. This summation represents the aggregate signal received by the cell. However, a weighted sum alone is insufficient for decision-making because it lacks a baseline threshold. Without a baseline, even tiny positive inputs could trigger a decision when all features happen to be zero. To resolve this, the neuron incorporates an independent internal parameter known as the bias. The bias functions as an adjustable offset or baseline threshold that is added directly to the weighted sum of inputs. Mathematically, the bias can be thought of as a weight attached to an imaginary constant input feature that is always equal to 1. Physically, the bias shifts the entire activation threshold of the neuron up or down regardless of the input values. If a neuron has a high negative bias, it demands an exceptionally strong positive weighted sum from its inputs before it will fire. Conversely, if a neuron has a high positive bias, it defaults to firing unless heavily suppressed by negative weighted inputs. To visualize this aggregate computation geometrically, consider the vector space formed by the input features. If we have two input features, our inputs exist as points on a two-dimensional plane. The combination of incoming weights and the scalar bias defines a straight line running across that plane. This line is known as a decision boundary. Inputs falling on one side of the line yield a positive weighted sum plus bias, while inputs falling on the opposite side yield a negative value. If we expand our system to 3 input features, the decision boundary expands from a line into a two-dimensional flat plane cutting through a three-dimensional space. In higher dimensions with hundreds of features, this boundary is called a decision hyperplane. The primary job of a single neuron is to position this hyperplane through space such that it separates data points belonging to one outcome class from data points belonging to another. Once the neuron calculates the scalar result of the weighted sum plus bias, it passes this raw value through a mathematical function called an activation function. In the classic perceptron model, this activation function takes the form of a hard step function. The hard step function acts as a binary switch. If the calculated sum plus bias is greater than or equal to 0, the function outputs a value of 1, indicating that the neuron has fired or activated. If the value is strictly less than 0, the function outputs a value of 0, indicating that the neuron remains silent. This brings us to the fundamental question of learning. How does a perceptron automatically adjust its weights and bias so that its decision hyperplane correctly separates different classes of data? Learning in a perceptron occurs through an iterative error-driven update process known as the perceptron learning rule. We begin by initializing all weights and the bias to arbitrary small values, effectively placing the decision hyperplane in a random position across the feature space. We then feed a label training sample through the neuron and compare its predicted binary output against the true target label. If the neuron's prediction matches the target label, no error has occurred. The decision hyperplane successfully categorized the sample, and we leave the weights and bias completely unchanged. However, if the prediction is incorrect, an error exists, and the neuron must adjust its internal parameters to pull the hyperplane closer to a correct orientation. There are two distinct failure modes in binary classification. A false positive, where the neuron predicted 1 when the correct label was 0, and a false negative, where the neuron predicted 0 when the correct label was 1. Consider the false negative scenario first. The neuron outputted 0 because its weighted sum plus bias fell below the 0 threshold, yet the true target was 1. To correct this, the neuron needs to increase its weighted sum for this specific input pattern. The perceptron learning rule achieves this by taking the vector of input features, multiplying each feature by a small positive scaling factor called the learning rate, and adding these scaled feature values directly to their corresponding weights. Simultaneously, the bias is increased by the learning rate. Because the inputs that led to the false negative were positive, adding them to the weight vector aligns the weight vector more closely with the input vector, increasing their dot product. As a result, the next time the neuron sees a similar input pattern, its calculated weighted sum will be higher, pushing the result closer to or across the activation threshold. Conversely, consider a false positive scenario. The neuron outputted 1 because its weighted sum plus bias exceeded 0, but the true label was 0. The neuron must decrease its response to this input pattern. The learning rule handles this by subtracting the scaled input feature values from their corresponding weights, while also subtracting the learning rate from the bias. Subtracting the input vector rotates the weight vector away from the input vector, reducing their dot product and driving the weighted sum lower. This parameter update mechanism operates under a remarkable mathematical guarantee known as the Perceptron convergence theorem. The theorem proves that if a dataset is linearly separable, meaning there exists at least one geometric hyperplane that can perfectly divide the positive data points from the negative data points without a single error, then the perceptron learning rule is guaranteed to find such a boundary in a finite number of steps, regardless of the initial weight values. The algorithm will iterate through the training data, continually tweaking the orientation and offset of its hyperplane whenever it encounters a misclassified point, until eventually every point lies on the correct side of the boundary and no further updates occur. Despite this powerful convergence proof, the single neuron perceptron possesses a catastrophic structural limitation that severely restricted early machine learning architectures. It can only classify linearly separable data. If the true underlying boundary between two classes is curved, circular, or fragmented into separate disjoint regions, a single linear hyperplane cannot separate them without committing errors. The most famous demonstration of this limitation is the exclusive or logical operation, commonly referred to as the XOR problem. Consider a simple logical system with two binary inputs, where the target output should be 1 if exactly one of the inputs is true, but 0 if both inputs are false or both inputs are true. If we plot these 4 possible input combinations on a two-dimensional grid, the points where both inputs are identical 0, 0 and 1, 1 belong to class 0. The points where the inputs differ 0, 1 and 1, 0 belong to class 1. If you attempt to draw a single straight line across this grid to isolate the class 1 points from the class 0 points, you will immediately discover that it is physically impossible. Any line that separates 0, 1 from 0, 0 will inevitably group 0, 1 with 1, 1 or misclassify 1, 0. The data points form a diagonal cross pattern that defies linear separation. Because a single artificial neuron can only compute a single linear combination of its inputs followed by a step function, it is mathematically incapable of solving the XOR function. To overcome this linear separability bottleneck, computer scientists and engineers realized that systems needed to combine multiple decision boundaries. Just as a single straight line cannot isolate a complex region on a map, a single neuron cannot isolate nonlinear feature distributions. However, if you place 2 distinct lines on a plane, you can create an angle or a strip between them. If you add a third line, you can enclose a triangle. By combining multiple linear boundaries, you can carve out bounded geometric shapes of arbitrary complexity. This key architectural realization transitioned research away from isolated single neuron models toward multi-layer neural networks. In a multi-layer network, an initial layer of neurons computes multiple independent linear decision hyperplanes across the input space. Subsequent layers take the outputs of those first-layer neurons as their input features, effectively performing logical combinations like and, or, and not over the geometric regions defined by the first layer. Through layer stacking, a neural network transforms the original input feature space into a new coordinate representation where non-linearly separable problems become linearly separable. Before we explore multi-layer architectures in detail, it is critical to understand the mathematical mechanics of feature weighting and bias interaction. The weight vector determines the orientation or angle of the decision hyperplane in space, while the bias determines the perpendicular distance from the origin to that hyperplane. If we set the bias to 0, the decision hyperplane is forced to pass directly through the origin point of the coordinate system. This severely constrains the model because many real-world classification boundaries do not intersect the origin. By allowing the bias to be learned alongside the weight vector, the network gains the freedom to translate the decision boundary anywhere in feature space. Furthermore, we must evaluate the sensitivity of the single neuron model to feature scaling. If one input feature is measured in thousands, such as annual salary in dollars, while another input feature is measured in small units, such as age in decades, the magnitude of the features drastically impacts the gradient and update steps. The feature with the larger raw numbers will dominate the weighted sum calculation even if its weight is small. During weight updates, larger inputs cause massive jumps in parameter space, while smaller inputs cause tiny, negligible updates. To prevent this instability, modern engineering practices always normalize input features so that all dimensions share comparable scales, typically by subtracting the mean and dividing by the standard deviation across the dataset. Another crucial aspect of single neuron mechanics is the geometric concept of vector projection. The weighted sum calculation can be rewritten as the dot product between the weight vector and the input vector. Geometrically, the dot product equals the magnitude of the input vector multiplied by the magnitude of the weight vector, multiplied by the cosine of the angle between them. This means a neuron acts as a pattern matching detector. The weighted output is highest when the directional orientation of the input feature vector aligns perfectly with the orientation of the neuron's learned weight vector. When an incoming input vector points in the exact same direction as the weight vector, the cosine of the angle is 1, producing the maximum possible positive value. When the input vector is orthogonal or perpendicular to the weight vector, the dot product is 0. When the input points in the opposite direction, the dot product becomes negative. In this sense, learning the weight vector of a single neuron corresponds to discovering a canonical feature prototype or template. The neuron continuously compares incoming signals against this internal template. If an incoming signal resembles the stored template, the neuron produces a high activation value. If the signal deviates from the template, the activation drops. This template matching perspective makes it intuitive why a single neuron fails on complex tasks like visual object recognition or natural language understanding. A single template cannot capture all variations of a complex category. A single neuron trying to recognize handwritten digits, for example, would have to learn one average weight template for the digit 8. However, if people write the digit 8 in different styles with varying slants or loop sizes, an average template becomes a blurry, low-confidence match for all of them. Solving complex real-world pattern recognition requires an ensemble of specialized feature detectors working in parallel, where each individual neuron learns to detect a specific subcomponent or edge of a pattern. One neuron might activate when a vertical curve is detected, another might activate when a horizontal line is present, and a downstream neuron integrates these subcomponent activations to render a final decision. This brings us directly to the concept of feedforward neural network architecture, where multiple neurons are arranged into layered computational cascades capable of representing arbitrary nonlinear functions. Having established how a single neuron functions as a linear decision boundary, we now expand our perspective to multilayer feedforward neural networks, commonly referred to as multilayer perceptrons or deep dense networks. A single neuron is a powerful linear pattern classifier, but as we observed with the exclusive or problem, real-world data distributions are almost never linearly separable. To model complex, nonlinear relationships, we must assemble individual neurons into structured networks where signals cascade sequentially from an input layer, through one or more hidden layers, and finally into an output layer. To build a clean mental model of a feedforward neural network, visualize a multi-stage assembly line operating inside a modern manufacturing facility. At the beginning of the line stands the input layer. The input layer does not perform any mathematical processing or parameter multiplication. It functions purely as an entry portal or receiver for raw numerical data. If we are processing a digital image, the input layer consists of an array of nodes where each node receives the numerical intensity of a single pixel. If we are processing tabular data, each input node receives a single scalar feature, such as temperature, pressure, or geographical coordinates. From the input layer, data signals travel forward along thousands of directed connections toward the first hidden layer. The term hidden layer does not imply mystery or secrecy. It simply means that the activations produced within these intermediate stages are not directly observed as final system outputs. They represent internal representation states constructed by the network to solve the task. Every neuron in the first hidden layer receives connections from all nodes in the input layer. When every node in one layer connects to every node in the subsequent layer, the layer is called a fully connected or dense layer. Inside each hidden neuron, the exact same fundamental computation occurs that we examined in the single neuron model. Incoming feature signals are scaled by individual connection weights, aggregated into a total sum, offset by a scalar bias, and passed through a nonlinear activation function. However, because multiple neurons operate in parallel within a single hidden layer, we can represent this entire layer-wide computation using high-level matrix algebra rather than writing thousands of individual scalar equations. Imagine stacking all input features into a single horizontal row vector. If we have 10 input features, our input is a 1 by 10 vector. Now consider a hidden layer containing 20 neurons. Each individual neuron possesses its own unique weight vector consisting of 10 numbers, corresponding to the 10 input features it receives. If we stack all 20 of these 10-element weight vectors vertically, we form a two-dimensional weight matrix with 10 rows and 20 columns. When we perform matrix multiplication between our 1 by 10 input vector and our 10 by 20 weight matrix, the rules of linear algebra compute the dot product between the input vector and every single neuron's weight vector simultaneously in a single parallel operation. The result of this matrix multiplication is a new 1 by 20 row vector containing the unactivated sum for each of the 20 hidden neurons. We then add a 1 by 20 bias row vector, performing an element-wise addition that applies each neuron's specific bias offset. Finally, we pass each of these 20 scalar values through a nonlinear activation function, producing a final 1 by 20 row vector of hidden layer activations. This sequence of operations, matrix multiplication by a weight matrix, vector addition of a bias vector, and element-wise evaluation of an activation function, constitutes the standard forward-pass transformation performed by every dense layer in a neural network. Understanding this feed-forward operation from a geometric perspective reveals why deep neural networks are so remarkably effective. A matrix multiplication represents a linear coordinate transformation in space. Depending on the values inside the weight matrix, this transformation can rotate, stretch, compress, or skew the input feature space. Adding the bias vector performs a translation, shifting the coordinate space across dimensions. Passing the result through a nonlinear activation function introduces nonlinear bends, folds, and warps into the feature space. Therefore, each hidden layer in a feed-forward neural network acts as a spatial warping engine. The first hidden layer takes the original raw feature space, stretches it, rotates it, and warps it into a new intermediate representation space. The second hidden layer takes that intermediate space and warps it further into a third representation space. The primary objective of the entire network during training is to discover weight matrices and bias vectors that warp the input space so dramatically that complex, tangled, non-linearly separable data distributions are unraveled into clean, linearly separable clusters by the time they reach the final output layer. Consider our previous XOR example to visualize this spatial warping in action. In its raw two-dimensional input space, the XOR points 0, 0, and 1, 1 are diagonally opposite each other, making linear separation impossible. However, when we pass these 4 points through a hidden layer with 2 neurons using appropriate nonlinear activations, the hidden layer maps the 4 points into a new two-dimensional hidden feature space. In this new hidden coordinate space, the point 0, 0 remains near the origin, but the point 1, 1 is folded over and mapped to a position that aligns with 0, 0, while 0, 1 and 1, 1 are pushed into distinct regions. What was originally an unseparable cross pattern in the input space becomes a cleanly separable distribution in the hidden feature space, allowing a final output neuron to separate them with a single straight line. This spatial warping perspective highlights the profound concept of representation learning. In traditional machine learning paradigms, human software engineers spent immense effort manually crafting domain-specific features, such as calculating custom ratios, extracting edge frequencies from images, or applying Fourier transforms to make data linearly separable for simple algorithms. In deep learning, human feature engineering is replaced by automated hierarchical feature discovery. The lower layers of a deep network learn primitive, low-level representations, such as detecting sharp gradients or color transitions in visual data. Intermediate layers combine those primitives into mid-level concepts, such as textures, corners, and simple geometric shapes. Deeper layers combine mid-level concepts into high-level semantic representations, such as identifying eyes, wheels, or specific semantic words. This brings us to a fundamental architectural design choice: the trade-off between network width and network depth. Network width refers to the number of parallel neurons contained within a single layer, while network depth refers to the total number of stacked layers in the sequential chain. To evaluate this trade-off, we must examine a pivotal theoretical result known as the universal approximation theorem. The universal approximation theorem states that a feedforward neural network containing a single hidden layer with a finite number of neurons can approximate any continuous mathematical function on compact subsets of real space to arbitrary accuracy, provided the activation function is nonlinear and bounded. At first glance, this theorem might suggest that deep networks with many stacked layers are entirely unnecessary, since a wide, single hidden layer network can theoretically represent any continuous mapping. However, relying on extreme width rather than depth presents severe practical and computational bottlenecks. To approximate a complex, highly oscillatory, or high-dimensional function using a single hidden layer, the number of neurons required in that single layer expands exponentially with the dimension of the input space. A single-layer network attempting to memorize complex visual scenes would require trillions of parallel neurons, leading to massive parameter bloat, excessive memory footprint, and an extreme vulnerability to overfitting. Stacking multiple layers into a deep architecture solves this parameter explosion through compositional efficiency. When a network is deep, each additional layer enables the system to compute compositions of previously learned functions. If a single layer can compute basic functions, 2 layers can compute functions of functions, 3 layers can compute functions of functions of functions, and so forth. Mathematically, a deep network with a relatively small number of total parameters distributed across many layers can express complex, highly compositional function spaces that would require an exponentially larger number of parameters in a single wide layer. To conceptualize this parameter efficiency, consider the analogy of origami paper folding. If you want to create a highly intricate three-dimensional shape out of a flat sheet of paper using a single fold, you can only make one straight crease across the page. To create a complex geometric sculpture with a single step, you would need an impossibly huge sheet of paper with an infinite number of simultaneous parallel cuts. However, if you allow a sequential chain of multiple simple folds, where each fold builds upon the result of the previous fold, a standard-sized piece of paper can be transformed into a complex shape in just a dozen sequential steps. Depth in a neural network is equivalent to sequential paper folding, enabling the model to construct intricate high-dimensional decision boundaries with a fraction of the total parameters. Despite the compositional superiority of deep networks, adding depth introduces severe engineering challenges during training. As signals cascade forward through dozens of stacked layers, matrix multiplications accumulate sequentially. If the spectral norm or magnitude of the weight matrices across layers is consistently less than 1, signal amplitudes decay exponentially as they pass through the network, causing deep activations to collapse to zero. Conversely, if the weight magnitudes are consistently greater than 1, signal amplitudes explode exponentially, causing numerical overflow and saturating activations. Managing signal flow, numerical stability, and information preservation across deep architectures requires careful initialization strategies, specialized activation functions, and residual skip connections, which we will analyze in subsequent sections. From an operational standpoint, the feedforward pass must also handle batch processing efficiently. In production environments, neural networks rarely process single data samples one at a time. Processing individual samples sequentially underutilizes modern hardware accelerators such as GPUs and TPUs, which are optimized for massive parallel matrix computations. Instead, training and inference pipelines group multiple individual data samples into a single structure called a mini-batch. If a mini-batch contains 64 distinct input samples, and each sample consists of 10 features, we stack these samples vertically to construct a two-dimensional batch matrix of shape 64 by 10. When we multiply this 64 by 10 batch matrix by our 10 by 20 weight matrix, modern hardware performs matrix-matrix multiplication, computing the hidden activations for all 64 samples simultaneously in parallel execution units. The resulting output matrix has a shape of 64 by 20, where each row represents the intermediate hidden activations for one corresponding input sample in the batch. This batch matrix operation necessitates broadcasting during vector addition. When we add our 1 by 20 bias row vector to the 64 by 20 matrix result, the computational engine automatically replicates or broadcasts the bias vector across all 64 rows. Every sample in the batch receives the exact same bias offset for corresponding hidden neurons. Efficient batch matrix multiplication and vector broadcasting form the computational backbone of high-throughput deep learning engines. Finally, we must consider the terminal stage of a feedforward neural network, the output layer. The structural design of the output layer depends entirely on the specific machine learning task the network is designed to perform. If the task is scalar regression, such as predicting the market price of a house or estimating ambient temperature, the output layer consists of a single neuron without any nonlinear activation function, producing an unbounded continuous real number. If the task is binary classification, the output layer consists of a single neuron paired with a sigmoid activation function that squeezes the real-valued score into a probability range between 0 and 1. If the task is multi-class classification, such as identifying which of 10 possible handwritten digits an image represents, the output layer contains 10 distinct neurons, one for each class, paired with a softmax activation function that normalizes raw output scores into a joint probability distribution where all outputs sum to 1. Having examined the structural topology and forward computational cascade of feedforward neural networks, we must now investigate the crucial nonlinear components that make deep representation learning possible: activation functions and their mathematical properties. To appreciate the critical role that activation functions play in deep learning architectures, we must first confront a fundamental mathematical reality. Without nonlinear activation functions, even a network with 100 hidden layers collapses into a simple linear model. To understand why this collapse occurs, consider a multilayer network where every neuron omits its activation function, or uses a simple linear identity function where the output equals the raw weighted sum plus bias. In the first hidden layer, the activation vector is computed as the input matrix multiplied by the first weight matrix plus the first bias vector. In the second hidden layer, This first layer activation is multiplied by the second weight matrix plus the second bias vector. If you substitute the equation of the first layer directly into the equation of the second layer and apply the algebraic distributive property, you will discover that the product of the two weight matrices can be multiplied together ahead of time into a single combined weight matrix. Similarly, the biases collapse into a single combined bias vector. No matter how many hidden layers you stack in sequence, whether 5, 50, or 500, if all intermediate operations are linear, the entire chain of matrix multiplications reduces mathematically to a single matrix multiplication followed by a single vector addition. The deep network is structurally incapable of forming curved decision boundaries or learning nonlinear relationships. It becomes functionally identical to a basic single-layer linear model. Nonlinear activation functions are the sole component that breaks this linear collapse, granting deep networks the mathematical capacity to bend, fold, and warp feature space to approximate complex real-world target functions. Historically, early neural network designs attempted to introduce nonlinearity using the binary hard step function inherited from the classic perceptron. However, the hard step function introduces a fatal barrier to gradient-based optimization. Its derivative is zero everywhere along its horizontal flat segments, and it is completely undefined at the exact point of step transition, because optimization algorithms rely on calculating derivatives to determine which direction to adjust weights. A function with zero derivative provides no gradient information whatsoever. Small changes to incoming weights produce zero change in output until the input crosses the step threshold, at which point the output instantly jumps. A model cannot learn incrementally using zero gradients, rendering the hard step function unusable for modern backpropagation training. To enable gradient-based learning, researchers shifted to smooth, continuously differentiable activation functions, beginning with the sigmoid activation function. The sigmoid function takes any real-valued number from -infinity to +infinity and maps it smoothly into a bounded range between 0 and 1, producing a distinctive S-shaped curve. Small input values near 0 map to values close to 0.5, large positive inputs approach 1, and large negative inputs approach 0. The sigmoid function possesses an attractive probabilistic interpretation. Because its output is strictly bounded between 0 and 1, the value can be directly interpreted as a confidence score or probability estimate that a given input belongs to a positive class. This property makes sigmoid the standard activation function for the final output neuron in binary classification networks. Furthermore, sigmoid has an extraordinarily convenient mathematical derivative. The derivative of the sigmoid function evaluated at a point equals the sigmoid value itself multiplied by 1 minus the sigmoid value. However, when applied inside the hidden layers of deep networks, the sigmoid function introduces two severe engineering flaws: the vanishing gradient problem and non-zero-centered outputs. To understand the vanishing gradient problem in sigmoid units, examine the shape of its mathematical derivative. The maximum value of the sigmoid derivative occurs at an input of 0, where the derivative reaches its absolute peak of only 0.25. As the input value moves away from 0 in either direction, becoming a moderately large positive number like +5 or a negative number like -5, the sigmoid curve flattens out into horizontal saturation regions. In these saturated regions, the slope of the curve approaches 0, causing the derivative to plummet towards 0. During backpropagation, error gradients flowing backward through the network are sequentially multiplied by the derivative of each layer's activation function. If a deep network has 10 hidden layers using sigmoid activations, The backward gradient pass involves multiplying 10 derivative values together in a continuous chain. Because each sigmoid derivative is at most 0.25, and frequently much smaller when saturated, multiplying these small fractions together causes the gradient amplitude to shrink exponentially as it travels backward toward the earlier layers. By the time the gradient reaches the initial input layers, it has decayed to near zero. As a result, the weights in the early layers of the network receive virtually no update signal, remaining stuck in their initial random states while the later layers overfit. The second structural drawback of the sigmoid function is that its output values are strictly positive, ranging from 0 to 1. When a hidden layer produces exclusively positive activation values, these positive numbers become the input features for the subsequent layer. During backpropagation, the derivative of the loss with respect to the weights in that subsequent layer depends directly on these incoming positive input values. Consequently, all gradient updates for those weights are forced to share the exact same algebraic sign, either all positive or all negative, depending on the sign of the incoming error signal. This constraint prevents the weights from being updated independently in their optimal directions, forcing the parameter vector to follow an inefficient, zigzagging trajectory through parameter space during training, slowing down convergence significantly. To resolve the non-zero-centered output problem of sigmoid, researchers introduced the hyperbolic tangent activation function, commonly abbreviated as TAN. The TAN function is mathematically a scaled and shifted version of the sigmoid curve, mapping any real-valued input into a symmetric range between -1 and +1. When the input to a TAN function is 0, the output is exactly 0. Inputs greater than 0 yield positive outputs, while inputs less than 0 yield negative outputs. Because TAN outputs are centered around 0, the average activation value flowing into subsequent layers stays close to 0 throughout training. This allows gradient updates to take both positive and negative values independently, eliminating the inefficient zigzagging weight trajectories associated with sigmoid activations. Additionally, the maximum derivative of the TAN function occurs at 0, where its slope reaches 1.0, which is 4 times larger than the peak derivative of sigmoid. Despite these improvements, TAN remains a saturating activation function. As input values become moderately large in magnitude, exceeding +3 or falling below -3, the TAN curve flattens into horizontal saturation plateaus where its derivative approaches 0. While TAN mitigates vanishing gradients compared to sigmoid in shallow networks, it still suffers from severe gradient vanishing when stacked across deep multi-layer architectures. The major breakthrough that enabled the successful training of modern deep neural networks was the introduction of the rectified linear unit, universally known as ReLU. The ReLU activation function abandons complex exponential curves in favor of a piecewise linear function with an extraordinarily simple definition. If the input is less than or equal to 0, the output is 0. If the input is strictly positive, the output equals the input itself. The simplicity of ReLU delivers 2 profound architectural advantages: computational efficiency and non-saturating gradients. Computing the ReLU function requires no expensive exponential calculations or division operations. It simply requires a hardware-level conditional check or max operation against 0, executing orders of magnitude faster on processor hardware. More importantly, ReLU completely solves the vanishing gradient problem for positive input values. For any positive input, the slope of the ReLU function is exactly equal to 1.0, regardless of how large the input becomes. When gradients are backpropagated through a chain of active positive ReLU units, Multiplying by a derivative of 1.0 preserves the gradient magnitude perfectly, allowing strong error signals to travel backward through dozens or hundreds of layers without decaying. However, RealU introduces its own distinct vulnerability known as the dying RealU problem. Because RealU outputs 0 for any negative input, the derivative of RealU for all negative inputs is strictly 0. If a large gradient update during training adjusts a neuron's weights and bias such that the neuron produces negative weighted sums for all samples in the training dataset, that neuron enters a state of permanent inactivity. When a neuron produces negative inputs for all data samples, its output is 0, and its derivative is 0 during every backward pass. Because the derivative is 0, no gradient can pass backward through the neuron, and its weights receive 0 updates during subsequent training steps. The neuron becomes functionally dead, locked into a permanent state where it outputs 0 and never recovers. In large networks, a significant percentage of RealU neurons, sometimes 20 to 40%, can die during training, reducing the effective capacity of the network and wasting memory allocations. To remedy the dying RealU problem, several parametric variants were engineered to ensure that negative inputs retain a small, non-zero gradient flow. The most prominent variant is leaky RealU. Leaky RealU modifies the zero region for negative inputs by introducing a small positive slope, typically 0.01. If the input is positive, leaky RealU behaves like standard RealU, returning the input directly with a slope of 1.0. If the input is negative, leaky RealU multiplies the input by 0.01, returning a small negative output with a constant slope of 0.01. By maintaining a non-zero slope for negative inputs, leaky RealU ensures that even when a neuron is inactive, a further generalization of leaky RealU is parametric RealU, often abbreviated as PRealU. Instead of hard-coding the negative slope to a fixed constant like 0.01, parametric RealU treats the negative slope coefficient as a learnable parameter. Each neuron or layer possesses its own slope parameter, which is updated automatically via gradient descent during training alongside the connection weights and biases. This allows the network to dynamically learn whether a specific feature detector benefits from a steep negative slope, a shallow negative slope, or no negative slope at all. Another sophisticated alternative design to combine the non-saturating benefits of RealU with zero-centered smooth curves is the exponential linear unit, or ELU. For positive inputs, ELU behaves like RealU, returning the input directly. For negative inputs, ELU uses an exponential curve that smoothly saturates to a negative threshold, typically negative 1.0. ELU brings the average activation value closer to 0 while maintaining a smooth, continuous derivative across all inputs, improving noise robustness and convergence speed, though at the cost of computing exponential functions during the forward pass. In modern deep learning architectures, particularly state-of-the-art natural language processing models and vision transformers, two advanced activation functions have achieved widespread adoption: the Gaussian error linear unit, known as GELU, and the swish activation function. GELU introduces a probabilistic perspective to feature activation. Instead of applying a deterministic threshold check like RealU, GELU scales an incoming input by the cumulative distribution function of a standard normal distribution. Intuitively, GELU acts as a soft, probabilistic gate. Inputs with large positive values are passed through almost unchanged with high probability, while large negative values are suppressed toward 0. For intermediate values near 0, GELU forms a smooth, non-monotonic curve that dips slightly below 0 before curving upward. This smooth, non-monotonic curvature allows GELU to preserve tiny negative gradient signals while avoiding sharp mathematical corners, yielding superior generalization performance in deep transformer networks. Similarly, swish is a self-gated activation function defined as the input value multiplied by the sigmoid of the input value scaled by a constant factor. Like GELU, swish forms a smooth, non-monotonic curve that dips slightly below zero for small negative inputs before approaching zero for large negative values, while growing linearly for positive inputs. Empirical benchmarking across complex computer vision and sequence modeling tasks demonstrates that replacing ReLU with GELU or swish consistently improves final model accuracy in deep architectures. To conclude our analysis of activation functions, we must examine the softmax activation function, which plays a specialized, critical role in multi-class classification networks. In a multi-class classification problem where an input must be assigned to one of several mutually exclusive categories, such as classifying an image into one of 100 animal species, the final linear layer of the neural network produces a vector of unnormalized real-valued scores, commonly referred to as logits. Logits can take any positive or negative real numbers, making them impossible to interpret directly as probabilities. The softmax activation function takes this vector of raw logits and transforms it into a valid probability distribution. The operation proceeds in two steps. First, it applies the natural exponential function to each individual logit in the vector. Exponentiation forces all negative logits to become positive real numbers, while exponentially amplifying larger logits relative to smaller ones. Second, it sums all the exponentiated values together across all classes to compute a global normalization denominator and divides each individual exponentiated value by this sum. The resulting vector of softmax outputs satisfies all mathematical criteria of a joint probability distribution. Every output value is strictly between 0 and 1, and the sum of all output probabilities across all categories equals exactly 1.0. Each output can be directly interpreted as the network's estimated probability that the given input belongs to that specific category. However, implementing softmax in production systems requires careful numerical stability safeguards to prevent numerical overflow and underflow. When raw logits contain large positive numbers, such as a logit value of 800, computing the natural exponential of 800 causes floating point overflow, resulting in infinite values that crash training runs. Conversely, if all logits are large negative numbers, exponentiation produces zero values that lead to division by zero errors. To solve this numerical instability, software engines employ a mathematically equivalent technique called the logsum exp trick. Before exponentiating the logits, the system identifies the maximum logit value present in the current sample's logit vector and subtracts this maximum scalar value from every logit in the vector. Because subtracting a constant scalar from all inputs in both the numerator and denominator of the softmax equation cancels out algebraically, the resulting output probabilities remain completely identical. However, subtracting the maximum logit ensures that the largest logit in the adjusted vector becomes 0, preventing floating point overflow while maintaining pristine numerical precision. Understanding how activation functions introduce nonlinearity and shape output distributions brings us to the core engine of deep learning optimization, the backpropagation algorithm. The backpropagation algorithm, short for backward propagation of errors, is arguably the single most important algorithm in deep learning. Without backpropagation, training deep neural networks containing millions or billions of parameters would be computationally impossible. At its core, backpropagation solves the fundamental engineering challenge known as the credit assignment problem. Given a complex network with dozens of stacked layers and millions of internal weights, when the network makes an incorrect prediction at the output layer, how do we determine the precise degree of responsibility each individual weight in every layer bears for that final error? To understand how backpropagation solves credit assignment with mathematical precision, we must conceptualize a neural network as a directed computational graph. In a computational graph, nodes represent numerical quantities such as input scalars, weight matrices, bias vectors, intermediate weighted sums, and activation values, while directed edges represent basic mathematical operations such as addition, matrix multiplication, exponentiation, or activation evaluations. Data flows strictly forward through this graph from left to right during the forward pass, culminating in a single final scalar node representing the total loss or error of the model. Consider the forward pass first. During the forward pass, input feature vectors enter the graph at the far left. As data cascades forward through intermediate nodes, the network computes and stores two distinct categories of values at every single layer: pre-activation values, which represent the raw weighted sums plus biases, and post-activation values, which represent the results of applying activation functions to those pre-activation values. The system evaluates these nodes sequentially until it reaches the final output layer, computes the predicted output, compares that prediction against the true target label using a loss function, and outputs a single scalar loss value. Once the scalar loss is calculated at the final node, the forward pass is complete. However, to update the network's weights and reduce the loss, we need to calculate the exact partial derivative of the scalar loss with respect to every weight matrix and bias vector across every layer of the network. A partial derivative measures the rate of change of the loss with respect to a tiny change in a specific weight. It tells us both the direction and magnitude of parameter adjustment. If the partial derivative of the loss with respect to a weight is positive, increasing the weight will increase the loss, so we must decrease the weight to reduce error. If the derivative is negative, increasing the weight will decrease the loss. Calculating these partial derivatives directly across a deep graph using traditional calculus rules appears daunting because early weights are separated from the final loss node by dozens of intermediate transformations. Backpropagation solves this by applying the multivariable calculus chain rule in reverse, traversing the computational graph backward from the final loss node to the initial input layer. The chain rule states that if a scalar variable depends on an intermediate variable, which in turn depends on an initial input variable, the rate of change of the final scalar with respect to the initial input equals the product of the individual rates of change along the path. In simpler terms, to find how a tiny change at the beginning of a multi-stage chain affects the final output, you simply multiply together the local slopes of every intermediate link in the chain. The genius of backpropagation lies in how it modularizes this chain calculation through local gradient computation. Imagine standing at an arbitrary intermediate node inside a computational graph. This node performs a specific mathematical operation, taking one or two incoming inputs and producing an output value. To participate in backpropagation, this node only needs to understand two things. First, the local derivatives of its own operation with respect to its immediate inputs, and second, an incoming gradient value flowing backward from upstream nodes. During the backward pass, an upstream node sends a gradient value back down the edge. This incoming upstream gradient represents the derivative of the total scalar loss with respect to the output of our local node. Our local node immediately multiplies this incoming upstream gradient by its own local derivative to compute the downstream gradient. It then passes this newly computed downstream gradient backward to whichever nodes supplied its input signals. By repeating this simple local multiplication at every node in reverse topological order, error signals flow backward through the network like water reversing through a pipe system. Every node receives an incoming gradient from above, scales it by its local slope, and distributes the resulting gradient signal backward to the preceding layer. To ground this abstract computational graph mechanics in precise step-by-step mathematical reasoning, let us trace backpropagation explicitly through a feedforward network containing an input layer, a single hidden layer, and an output layer, following the classic formulation detailed by Goodfellow and other pioneering researchers. We begin at the far right of the computational graph, where the scalar loss function evaluates the discrepancy between the network's predicted output vector and the true target label vector. The first step of backpropagation is to calculate the derivative of the loss function with respect to the raw, unactivated logits of the output layer. We denote this initial output error term as delta output. For standard loss functions paired with their natural output activation functions, such as mean squared error paired with linear outputs, or cross-entropy loss paired with softmax or sigmoid outputs, this output delta simplifies to a remarkably clean expression. It is simply the vector difference between the predicted output probabilities and the true target labels. This difference vector represents the raw residual error of the network. If the predicted output matches the true target perfectly, the residual error vector is 0, generating 0 gradient. If there is a large discrepancy, the residual error vector produces a large gradient magnitude proportional to the mistake. Once we possess the output delta vector, we use it to calculate the gradients for the final layer's parameter weights and biases. To find the derivative of the loss with respect to the output weight matrix, the algorithm performs a matrix multiplication between the transpose of the hidden layer activation vector and the output delta vector. To visualize why this matrix multiplication occurs, consider a single connection weight bridging a specific hidden neuron to a specific output neuron. How much does a tiny change in this weight impact the final loss? A tiny change in the weight is amplified by the activation value of the hidden neuron supplying the connection, and then impacts the loss through the output error delta. Therefore, the total gradient for that connection weight equals the hidden neuron's activation value multiplied by the output error delta. When we compute this across all parallel connections in the layer, taking the vector product of incoming hidden activations and outgoing error deltas yields the exact gradient matrix for the entire output weight layer. Simultaneously, the gradient for the output bias vector is computed. Because the bias is added directly to the weighted sum without being multiplied by any input activation, its local derivative is simply 1.0. Thus, the gradient of the loss with respect to the output bias vector equals the sum of the output delta vectors across all samples in the current minibatch. Having calculated the exact parameter gradients for the output layer, the algorithm must now propagate the error signal backward across the boundary into the hidden layer. This step represents the core of the credit assignment mechanism. Once this backward projected error vector reaches the hidden layer, it represents the derivative of the loss with respect to the post-activation values of the hidden neurons. However, before this error can pass through the hidden neurons to reach their weights, it must pass backward through the hidden layer's activation function. To pass backward through an activation function, backpropagation performs an element-wise Hadamard product between the backward projected error vector and the derivative of the hidden activation function evaluated at the original pre-activation value stored during the forward pass. This step is where the mathematical properties of activation functions directly govern learning. If the hidden activation function is saturated, such as a sigmoid unit operating in its flat plateau region, its derivative is near zero. Multiplying the backward projected error vector by near-zero derivatives suppresses the incoming error signal, preventing it from traveling further. If the activation function is active, such as a positive real U unit with a derivative of 1.0, the error signal passes through completely unattenuated. The result of this element-wise multiplication is the hidden layer error delta vector, denoted as delta hidden. This delta hidden vector encapsulates the total responsibility that each hidden neuron bears for the final loss, accounting for both its outgoing weight strength and its activation slope. Finally, with delta hidden in hand, the algorithm computes the gradients for the hidden layer's weight matrix and bias vector using the exact same logic applied at the output layer. The gradient of the loss with respect to the hidden weight matrix is computed by multiplying the transpose of the initial input feature matrix by the delta hidden error vector. The gradient with respect to the hidden bias vector is computed by summing the delta hidden vectors across the mini-batch. If the network possessed additional hidden layers, such as 5 or 10 stacked layers, the algorithm simply repeats this exact same two-step recursive cycle. Project the error delta backward through the transposed weight matrix to the preceding layer, and multiply element-wise by the derivative of that layer's activation function to obtain the preceding layer's error delta. This recursive wave of backward error projection continues step by step until the algorithm reaches the initial input layer, at which point gradients for every weight and bias in the entire network have been computed. To appreciate why backpropagation is the cornerstone of modern deep learning software frameworks, we must evaluate its computational efficiency compared to alternative differentiation techniques, specifically numerical differentiation. Suppose a neural network contains 1 million parameters, and we wish to calculate the gradient of the loss with respect to every parameter. Using numerical differentiation, we would perturb a single parameter by a tiny delta value, run a complete forward pass through the entire network to measure the resulting change in scalar loss, divide the loss difference by delta to estimate the slope, and reset the parameter. To compute gradients for all 1 million parameters, we would be forced to execute 1 million distinct forward passes through the network. The computational complexity of numerical differentiation scales as order n squared, where n is the number of parameters. For modern networks containing millions or billions of parameters, numerical differentiation would require centuries of compute time for a single training step. Backpropagation, which represents a specialized implementation of reverse-mode automatic differentiation, eliminates this computational bottleneck entirely. In a single forward pass, backpropagation computes and caches all intermediate activations. In a single backward pass, traversing the graph in reverse, backpropagation computes the exact analytical gradients for all 1 million parameters simultaneously. The total computational complexity of backpropagation scales as order n, requiring roughly 2 to 3 times the compute operations of a single forward pass, regardless of whether the network has 10 parameters or 10 billion parameters. This algorithmic reduction from exponential complexity to linear complexity is what transforms deep learning from a theoretical concept into a scalable engineering discipline. However, backpropagation introduces a major operational constraint: memory footprint management. To compute the local activation derivatives during the backward pass, backpropagation requires access to the exact pre-activation and post-activation values calculated during the forward pass. Consequently, during forward execution, the system cannot discard intermediate layer activations. It must store every single tensor activation in accelerator memory until the backward pass completes for that batch. In extremely deep networks or large batch training pipelines, storing all intermediate activations across hundreds of layers consumes immense amounts of GPU memory, often causing out-of-memory crashes. To manage this memory pressure in production environments, software engineers implement a technique called activation checkpointing or gradient checkpointing. Gradient checkpointing trades compute operations for memory capacity. Instead of storing intermediate activations for every single layer in the network during the forward pass, the system only saves activation tensors at selective checkpoint layers, such as every 10th layer. During the backward pass, when the algorithm needs the intermediate activations for an uncheckpoint layer, it dynamically recomputes those missing activations on the fly by rerunning a local forward pass from the nearest preceding checkpoint. By selectively dropping and recomputing intermediate activations, gradient checkpointing reduces GPU memory overhead by up to 70%, enabling the training of massively deeper networks within hardware memory constraints. Now that we have established how backpropagation calculates exact parameter gradients across computational graphs, we must examine how optimization algorithms utilize these gradients to navigate complex loss landscapes and update network parameters. Having calculated exact parameter gradients using backpropagation, we now confront the fundamental question of optimization. How do we use these gradient vectors to navigate high-dimensional parameter spaces and guide a neural network toward minimal error? To visualize optimization intuitively, imagine the loss function of a neural network as a vast, high-dimensional landscape. If a network possesses two parameters, its loss landscape exists as a three-dimensional surface containing valleys, hills, ridges, and depressions, where the height of the terrain at any coordinate represents the scalar loss produced by those parameter values. In real-world deep networks containing millions of parameters, this loss landscape expands into a million-dimensional non-convex space. We cannot visualize a million dimensions visually, but the physical principles of navigation remain completely identical. Our goal during training is to find a coordinate set in parameter space that corresponds to the lowest possible altitude on this loss surface, known as a global minimum. However, because deep loss landscapes are highly non-convex, they are filled with treacherous terrain features. Flat plateaus where slopes vanish, steep narrow ravines where walls rise sharply on either side, high-altitude saddle points where the terrain slopes upward along some dimensions but downward along others, and millions of suboptimal local minima where the terrain dips temporarily before rising again. The primary navigation tool used to traverse this loss landscape is the gradient vector. Mathematically, the gradient vector of a loss function contains all the first-order partial derivatives of the loss with respect to every parameter in the network. The gradient vector possesses a crucial geometric property. It points in the direction of steepest descent, indicating which directional heading increases the loss at the fastest possible rate. Because our objective is to minimize loss rather than maximize it, optimization algorithms step in the exact opposite direction of the gradient vector. This fundamental optimization strategy is known as gradient descent. By taking a small step in the direction of the negative gradient vector, we move downhill toward lower loss altitudes. The basic gradient descent update rule evaluates the negative gradient vector, multiplies it by a positive scaling factor called the learning rate, and subtracts the resulting vector from the current parameter values. The learning rate is one of the most sensitive hyperparameters in deep learning. It governs the step size the optimizer takes down the mountain during each update step. If the learning rate is tuned too small, the optimizer takes microscopic steps downhill. Training becomes agonizingly slow, requiring millions of iterations to make progress, and the optimizer easily gets trapped in flat plateaus or high-altitude saddle points where tiny gradients cause progress to stall entirely. Conversely, if the learning rate is set too large, the optimizer takes massive, reckless leaps across the landscape. To apply gradient descent in software, we must decide how much training data to evaluate before computing a gradient step. This choice defines three distinct flavors of gradient descent: batch gradient descent, stochastic gradient descent, and mini-batch gradient descent. In batch gradient descent, the optimizer computes the loss and its corresponding gradient across the entire training dataset before performing a single parameter update. If a dataset contains 1 million training samples, batch gradient descent passes all 1 million samples forward through the network, averages their error gradients together, and takes one parameter step. The primary advantage of batch gradient descent is stability. Because the gradient is averaged over the entire dataset, the resulting update vector represents the true, deterministic direction of steepest descent for the global dataset loss. However, batch gradient descent presents severe engineering drawbacks. Passing millions of samples through a deep network for a single wait step is computationally slow and requires enormous GPU memory footprint to cache activations across the entire dataset. Furthermore, because the global loss surface is static, batch gradient descent is highly vulnerable to getting stuck in bad local minima or flat saddle points from which deterministic steps cannot escape. At the opposite extreme stands pure stochastic gradient descent, often abbreviated as SGD. Pure SGD evaluates a single training sample, computes its local gradient, and immediately updates the network parameters before moving to the next sample. Pure SGD executes extremely fast parameter updates and requires minimal memory footprint because only one sample is processed at a time. Moreover, because individual data samples possess unique noise characteristics, the loss landscape changes slightly from one sample to the next. This constant stochastic fluctuation introduces beneficial noise into the update trajectory, allowing the optimizer to bounce out of shallow local minima and flat saddle points. However, pure SGD introduces severe variance. Because individual training samples can contain noisy features or mislabeled outliers, individual gradient vectors point in wildly erratic directions. The parameter trajectory bounces violently through parameter space, oscillating back and forth rather than moving cleanly toward the minimum. While it converges faster than batch gradient descent in early training, pure SGD struggles to settle smoothly into exact optimal coordinates, hovering noisily around the minimum. To combine the deterministic stability of batch gradient descent with the computational speed and stochastic exploration of pure SGD, modern deep learning architectures rely almost exclusively on mini-batch gradient descent. Mini-batch gradient descent divides the training dataset into small, manageable subsets called mini-batches, typically containing between 32 and several thousand samples. The optimizer passes a single mini-batch forward through the network, averages the loss gradients across those specific samples, performs a parameter update step, and then moves to the subsequent mini-batch. Mini-batching achieves the ideal balance for modern parallel hardware. GPUs contain thousands of parallel processing cores optimized for matrix-matrix operations. Processing a mini-batch of 64 or 128 samples saturates GPU execution units efficiently, delivering high throughput. Simultaneously, averaging over a mini-batch smooths out individual sample noise, while preserving enough stochastic fluctuation to escape saddle points and explore complex loss landscapes. Despite the benefits of mini-batching, standard stochastic gradient descent faces severe structural challenges when navigating complex landscape topologies, particularly narrow ravines and ill-conditioned loss surfaces. In a narrow ravine, the loss surface slopes down sharply along the steep side walls, but slopes very gently along the valley floor toward the true minimum. Because the gradient vector always points in the direction of steepest slope, the gradients computed by standard SGD point almost entirely across the ravine from wall to wall, rather than along the gentle floor toward the goal. Consequently, standard SGD wastes computational energy oscillating wildly back and forth between the steep walls, making agonizingly slow progress along the valley floor. To overcome ravine oscillations and accelerate progress across flat plateaus, engineers introduced the momentum optimizer. The momentum algorithm incorporates physical intuition drawn from classical mechanics. Imagine replacing the point-based optimizer with a heavy iron ball rolling down the lost landscape under the influence of gravity. As a physical ball rolls down a hill, it accumulates momentum and velocity. When it encounters small bumps, noisy fluctuations, or flat plateaus, its accumulated kinetic energy propels it forward continuously without stalling. When it enters a narrow ravine, the side-to-side forces acting on opposite walls cancel each other out algebraically over consecutive steps, while the consistent downhill forces along the valley floor accumulate velocity. In the momentum algorithm, the optimizer maintains an internal velocity vector alongside the parameter vector. During each update step, the new velocity vector is computed as a fraction of the previous velocity vector, governed by a momentum hyperparameter, typically set to 0.9, plus the scaled gradient of the current mini-batch. The parameters are then updated by subtracting this new velocity vector. The momentum coefficient acts as a friction parameter. If momentum is set to 0.9, 90% of the previous step's velocity is preserved into the current step. In flat regions where gradients are small, the accumulated velocity keeps the optimizer moving smoothly forward. In narrow ravines, high-frequency oscillations across opposing walls cancel out in the velocity accumulator, while consistent low-frequency gradients along the floor build up speed, propelling the optimizer toward the minimum up to 10 times faster than standard SGD. An elegant enhancement to standard momentum is Nesterov accelerated gradient, often called Nesterov momentum. Standard momentum calculates the current gradient at the optimizer's exact current position, and then applies the accumulated velocity vector to take a step. Nesterov momentum introduces a look-ahead predictive mechanism. Nesterov reasoned that since we already know the previous velocity vector will carry the optimizer forward by a certain amount, we should evaluate the gradient not at our current position, but at our anticipated future position, the position where the velocity vector would take us. The optimizer projects its position forward, calculates the gradient at that look-ahead location, and uses that future gradient to compute a corrective update. This look-ahead mechanism acts as an intelligent predictive braking system. If the accumulated velocity is propelling the optimizer rapidly toward a steep upward slope at the end of a valley, evaluating the gradient at the look-ahead position detects the rising slope before the optimizer actually lands there. The look-ahead gradient points strongly backward, reducing the velocity before the optimizer overshoots the valley floor, resulting in significantly reduced oscillations and superior convergence stability. While momentum and Nesterov accelerate learning by accounting for past directional velocity, they apply the exact same global learning rate to every single parameter in the network. In real-world neural networks, different parameters perform vastly different roles. Some parameters correspond to frequently occurring features that receive strong, consistent gradient updates during every step. Other parameters correspond to rare features that receive zero gradients for thousands of steps and brief, fleeting updates when rare samples appear. Using a single global learning rate presents a dilemma. If the learning rate is tuned for frequent features, rare feature weights receive microscopic updates and fail to learn. If the learning rate is increased for rare features, frequent feature weights receive massive updates and destabilize training. To resolve this, researchers developed adaptive learning rate algorithms that automatically scale the learning rate independently for each parameter based on historical gradient statistics. The pioneer of adaptive learning rate methods was AdaGrad, short for Adaptive Gradient Algorithm. AdaGrad maintains an internal running accumulator for every parameter in the network, which stores the cumulative sum of all past squared gradients for that specific weight. During parameter updates, AdaGrad divides the global learning rate by the square root of its historical squared gradient accumulator plus a tiny smoothing constant. If a parameter has received large, frequent gradients throughout training, its accumulated squared sum is huge. Dividing the learning rate by a large number shrinks the effective learning rate for that weight, preventing excessive updates. Conversely, if a parameter has received small or infrequent gradients, its accumulated sum remains tiny, keeping its effective learning rate large and allowing it to make rapid progress when gradients do arrive. AdaGrad excels at sparse feature learning, such as text processing where rare words appear infrequently. However, AdaGrad possesses a fatal structural flaw when applied to deep neural networks. Its squared gradient accumulator monotonically accumulates positive squared values without ever decreasing. As training progresses over thousands of steps, the historical sum inside AdaGrad grows larger and larger without bound. Dividing by an ever-increasing denominator causes the effective learning rate for every parameter to continuously shrink, eventually approaching absolute zero. Long before the network reaches an optimal minimum, the learning rate plummets to near zero, freezing parameter updates entirely and halting further learning. To fix AdaGrad's vanishing learning rate flaw, RMSProp, short for root mean square propagation, was created. RMSprop modifies AdaGrad's sum accumulator by replacing the monotonic sum with an exponentially decaying moving average of past squared gradients. Instead of adding raw squared gradients endlessly into an infinite sum, RMSprop scales the existing accumulator by a decay factor, typically 0.9, and adds 1 minus the decay factor multiplied by the current squared gradient. This exponential decay mechanism acts as a sliding historical window. The accumulator discards gradient information from thousands of steps ago, focusing primarily on the most recent gradient magnitudes. Because the exponential moving average does not grow infinitely, the effective learning rate in RMSprop does not plummet to zero. Parameters that previously experienced large gradients receive temporarily smaller learning rates to prevent instability, but as gradients settle, their effective learning rates recover smoothly. This adaptive mechanism allows RMSprop to navigate complex, non-stationary deep loss landscapes indefinitely without freezing. Building upon the insights of Momentum and RMSprop, researchers synthesized both paradigms into a unified, state-of-the-art optimization algorithm. Adaptive moment estimation, universally known as ADAM. ADAM combines the first moment of gradients, the exponentially decaying average of past gradients, inherited from Momentum, with the second raw moment of gradients, the exponentially decaying average of past squared gradients, inherited from RMSprop. ADAM maintains two internal tracking vectors for every parameter in the network. A first moment vector that tracks direction and velocity, and a second moment vector that tracks scale and variance. The first moment is updated using a decay hyperparameter called beta1, typically set to 0.9. The second moment is updated using a decay hyperparameter called beta2, typically set to 0.999. However, Adam's designers identified a subtle mathematical flaw during early training steps. Because both moment vectors are initialized to 0 vectors at the start of training, decaying them by 0.9 or 0.999 biases both moment estimates heavily towards 0 during initial steps. This 0 bias causes initial parameter updates to be artificially suppressed. To eliminate this initial suppression, Adam incorporates bias correction terms. Before updating parameters, the algorithm divides the first moment estimate by 1 minus beta 1 raised to the power of the current step number, and divides the second moment estimate by 1 minus beta 2 raised to the power of the current step number. In early steps, when the step number is small, these correction denominators scale up the moment estimates, ensuring unbiased gradient expectations from the very first iteration. The parameter update rule in Adam then divides the bias-corrected first moment estimate by the square root of the bias-corrected second moment estimate plus a tiny numerical stability constant, and multiplies the result by the global learning rate. Adam delivers remarkable empirical performance across virtually all deep learning domains. It automatically handles sparse gradients, adapts learning rates independently per parameter, dampens high-frequency oscillations, accelerates through flat plateaus, and remains robust against hyperparameter choices. Consequently, Adam has become the default first-choice optimizer for modern deep learning practitioners. However, when combining Adam with regularization techniques, specifically L2 weight decay, software engineers discovered a crucial mathematical discrepancy that led to the development of AdamW. In standard stochastic gradient descent, adding L2 weight decay, which penalizes large weights by adding a fraction of the weight magnitude to the loss function, is mathematically identical to directly shrinking parameter weights by a constant factor during each update step. However, when L2 weight decay is combined with Adam, the weight decay gradient is added directly into Adam's first and second moment accumulators. Because Adam divides updates by the square root of its second moment accumulator, weights with large historical gradients have their weight decay penalty artificially scaled down, while weights with tiny historical gradients have their weight decay penalty artificially scaled up. This distorts the intended weight decay penalty, causing large weights to evade regularization. AdamW corrects this distortion by decoupling weight decay entirely from the gradient moment accumulators. AdamW computes standard Adam moment steps using only the pure loss gradients, and then subtracts the decoupled weight decay penalty directly from the parameter vector as an independent step. Decoupling weight decay restores the true mathematical behavior of regularization, resulting in significantly superior generalization performance, particularly when training large language models and vision transformers. To deepen our mathematical intuition of automatic differentiation beyond scalar computational graphs, we must examine how backpropagation operates on higher-order multidimensional tensors using matrix calculus and Jacobian transformations. When a layer processes multidimensional tensors, such as a batch of feature representations, the local derivative of an output tensor with respect to an input tensor is formally defined by a Jacobian matrix. A Jacobian matrix organizes all first-order partial derivatives between every output element and every input element into a systematic grid. If an input tensor contains m elements and an output tensor contains n elements, the corresponding Jacobian matrix possesses n rows and m columns, where the entry at row I and column j represents the partial derivative of the ith output element with respect to the jth input element. In deep neural networks with large hidden dimensions, explicit construction of full Jacobian matrices would be computationally disastrous. For example, if a hidden layer maps a tensor of size 10,000 to another tensor of size 10,000, The full Jacobian matrix contains 100 million floating point elements. Allocating and storing full Jacobian matrices for every layer during backpropagation would instantly exhaust accelerator memory. Backpropagation bypasses explicit Jacobian matrix allocation entirely through vector Jacobian products, universally abbreviated as VJPs. In reverse mode automatic differentiation, the backward pass never requires the isolated Jacobian matrix alone. It only requires the product of the incoming upstream error gradient vector multiplied by the local Jacobian matrix. For standard neural network operations, such as matrix multiplications, element-wise activations, and convolutions, the vector Jacobian product can be evaluated analytically using compact, vector matrix operations without ever instantiating the massive intermediate Jacobian matrix in memory. To understand why reverse mode automatic differentiation is uniquely suited for neural network training compared to forward mode automatic differentiation, we evaluate their structural directional trade-offs. Automatic differentiation engines operate in two distinct modes: forward mode and reverse mode. Forward mode automatic differentiation computes derivatives concurrently with the forward pass, propagating directional derivative vectors, called tangent vectors, forward alongside function evaluations from left to right. If a system possesses n input variables and a single scalar output, forward mode automatic differentiation requires n distinct passes to evaluate the complete gradient vector, because each forward pass evaluates the derivative with respect to only one input variable at a time. Therefore, the computational complexity of forward mode automatic differentiation scales proportionally with the number of input parameters. Reverse mode automatic differentiation, which is the exact mathematical foundation of backpropagation, traverses the computational graph in the opposite direction. It executes a single forward pass to compute output values and cache intermediate nodes, followed by a single backward pass that propagates adjoint vectors backward from right to left. Crucially, a single backward pass in reverse mode automatic differentiation computes the exact partial derivatives of a scalar output with respect to all n input parameters simultaneously. The computational cost of reverse mode automatic differentiation scales with the number of output target dimensions, not the number of input parameters. Because neural network loss functions reduce millions or billions of parameters down to a single scalar loss value, one output dimension, reverse mode automatic differentiation evaluates the complete gradient vector for all parameters in a single backward pass. This structural asymmetry explains why deep learning frameworks are built entirely around reverse mode automatic differentiation engines. Inside reverse mode execution engines, the dynamic sequence of mathematical operations evaluated during the forward pass is recorded on an internal data structure called the Weingart list or execution tape. As Python or C code executes forward tensor operations, the framework pushes an operation node onto the execution tape. Each tape node stores pointers to the input tensors, a pointer to the output tensor, and a function pointer to the specific C++ or CUDA kernel that implements the vector Jacobian product for that operation. When the backward method is invoked on the scalar loss, the engine rewinds the execution tape, executing the recorded vector Jacobian product functions in strict reverse order, accumulating gradients inside each tensor's gradient buffer, and then clearing or preserving the tape based on framework settings. Having mastered how optimizers navigate loss landscapes, we must now examine the objective functions that generate these gradients. Loss functions tailored for specific machine learning tasks. Every time a neural network updates its internal weights through backpropagation, it relies entirely on a scalar metric known as a loss function, cost function, or objective function. The loss function functions as the sole compass guiding the optimizer through parameter space. It takes the network's predicted output vector, compares it directly against the ground truth target label, and outputs a single real-valued scalar that quantifies the total error committed by the model. Designing or selecting an appropriate loss function is one of the most critical decisions in system architecture. The loss function defines what the network cares about, what mistakes it heavily penalizes, and what trade-offs it accepts. If you choose an inappropriate loss function, the network will optimize its weights toward that flawed objective with mathematical ruthlessness, resulting in a model that performs poorly on true real-world goals. To understand how loss functions are constructed, we must examine their underlying statistical foundation, maximum likelihood estimation. Maximum likelihood estimation, or MLE, is a probabilistic framework for fitting models to data. Under MLE, we view the neural network not merely as a deterministic black box function, but as a conditional probability distribution generator. The network takes an input sample and computes the parameters of an assumed output probability distribution, such as the mean of a Gaussian distribution for continuous regression, or the event probabilities of a Bernoulli or categorical distribution for classification. The core principle of maximum likelihood estimation is to find parameter values that maximize the joint probability of observing the true dataset labels under our model's predicted distributions. In probability theory, multiplying thousands of individual sample probabilities together yields microscopic floating point numbers that trigger numerical underflow. To prevent underflow, we take the natural logarithm of the joint probability, transforming the product of probabilities into a sum of log probabilities. Because maximizing the log likelihood is mathematically equivalent to minimizing the negative log likelihood, deep learning architectures minimize the negative log likelihood of the data. Every standard loss function used in deep learning, from mean squared error to cross-entropy, is a direct mathematical realization of negative log likelihood minimization under specific distributional assumptions. We begin our detailed examination by evaluating loss functions engineered for regression tasks, where the target output is a continuous scalar or multidimensional real vector, such as predicting housing prices, stock volatility, or physical coordinates. The most widely used regression loss function is mean squared error, universally abbreviated as MSE or L2 loss. Mean squared error calculates the difference between the predicted scalar value and the ground truth target label for each sample, squares that difference, and averages the squared errors across all samples in the mini-batch. Squaring the prediction error delivers two crucial mathematical properties. First, squaring forces all error values to become positive real numbers, ensuring that positive errors and negative errors do not cancel each other out algebraically during batch averaging. Second, squaring penalizes larger errors disproportionately compared to smaller errors. To visualize this nonlinear penalty structure, consider a scenario where the network makes a small prediction error of 0.5 units. Squaring 0.5 yields a tiny loss penalty of 0.25. However, if the network makes a larger error of 10 units, squaring 10 yields a massive loss penalty of 100. The loss penalty grows quadratically with error magnitude. Under maximum likelihood estimation, minimizing mean squared error is mathematically equivalent to maximizing the log likelihood of the data under the assumption that prediction errors are normally distributed with constant variance around the true mean. Because MSE relies on quadratic error scaling, its mathematical derivative with respect to the prediction error is linear. The gradient magnitude is directly proportional to the difference between prediction and target. When the network's prediction is far from the target, it receives a huge gradient update that rapidly pulls the parameters toward the target. As the prediction approaches the target, the gradient shrinks smoothly to zero, allowing the optimizer to settle softly into the minimum without overshooting. However, mean squared error possesses a severe engineering vulnerability: extreme sensitivity to data outliers. In real-world datasets, such as financial transactions or sensor telemetry, corrupted data entries, measurement glitches, or rare extreme events can produce outlier target values that deviate wildly from the true underlying distribution. When an outlier target enters a mini-batch evaluated by MSE, the huge difference between the network's reasonable prediction and the extreme outlier value is squared. A single outlier with an error of 1,000 generates a squared loss penalty of 1 million. This single sample completely overwhelms the mini-batch gradient, forcing the optimizer to make massive parameter adjustments to accommodate the corrupted outlier, which severely degrades model accuracy on normal, valid data samples. To resolve MSE's vulnerability to outliers, architects utilize mean absolute error, abbreviated as MAE, or L1 loss. Mean absolute error calculates the absolute difference between the predicted scalar and the ground truth target label, without applying any exponentiation. Under maximum likelihood estimation, minimizing mean absolute error corresponds to maximizing the log likelihood under the assumption that prediction errors follow a Laplacian distribution, which possesses heavier tails than a standard Gaussian distribution. Because MAE measures absolute error, its penalty grows linearly rather than quadratically. An error of 10 units yields a loss penalty of 10. An error of 100 units yields a loss penalty of 100. An extreme outlier with an error of 1,000 generates a loss penalty of only 1,000, compared to 1 million under MSE. Consequently, MAE is vastly more robust to corrupted data and outliers, refusing to let extreme samples dominate parameter updates. However, mean absolute error introduces its own optimization drawback: a constant gradient magnitude and a non-differentiable point at zero error. The mathematical derivative of the absolute value function is constant. It equals +1 for any positive error and -1 for any negative error, regardless of how small or large the error is. When a model trained with MAE approaches very close to the true target, such as an error of 0.001, the gradient magnitude remains fixed at 1.0. Because the gradient does not shrink as error approaches zero, the optimizer takes constant-size steps, causing parameter values to overshoot and oscillate continuously back and forth across the target value rather than settling smoothly into exact optimal coordinates. Furthermore, at the exact point of zero error, the absolute value function has a sharp mathematical corner where the derivative is undefined, introducing instability in exact gradient engines. To combine the smooth, quadratic convergence of MSE near zero error with the robust, linear outlier tolerance of MAE for large errors, software engineers utilize the Huber loss, also known as smooth L1 loss. Huber loss incorporates a threshold hyperparameter, typically denoted as delta. When the absolute prediction error is less than or equal to delta, Huber loss functions identically to mean squared error, applying a smooth quadratic penalty whose gradient shrinks linearly towards zero as error approaches zero. When the absolute prediction error exceeds delta, Huber loss transitions smoothly into mean absolute error, applying a linear penalty whose gradient magnitude is capped at a constant value. By switching from quadratic scaling to linear scaling at the delta boundary, Huber loss prevents extreme outliers from generating. We now turn our attention from continuous regression tasks to classification tasks, where the target output is a discrete categorical label. For binary classification problems, where an input sample must be assigned to one of two mutually exclusive categories, such as classifying a transaction as fraudulent or legitimate, the standard objective function is binary cross-entropy loss, often abbreviated as BCE or log loss. Binary cross-entropy loss is grounded in information theory and Bernoulli distribution probability models. In binary classification, the final output neuron uses a sigmoid activation function to output a single scalar value between 0 and 1, representing the predicted probability that the sample belongs to class 1. The true ground truth label is represented as a binary indicator, 1 for class 1 and 0 for class 0. Binary cross-entropy evaluates two complementary logarithmic terms. If the true label is 1, the loss reduces to the negative natural logarithm of the predicted probability. If the true label is 0, the loss reduces to the negative natural logarithm of 1 minus the predicted probability. To build an intuitive mental model of binary cross-entropy, examine the behavior of the negative logarithm curve. The natural logarithm of 1.0 is exactly 0. Therefore, if the true label is 1 and the network predicts a probability of 1.0 with absolute confidence, the negative logarithm of 1 is 0, resulting in 0 loss penalty. As the network's predicted probability strays away from the true target of 1, dropping to 0.8, 0.5, or 0.1, the negative logarithm increases. Crucially, as the predicted probability approaches 0 for a true label of 1, the negative logarithm curve plummets toward negative infinity, causing the loss penalty to skyrocket toward positive infinity. This asymptotic penalty structure gives binary cross-entropy an essential engineering property. It inflicts extreme, near-infinite loss penalties on confidently wrong predictions. If the network outputs a probability of 0.001 for a sample whose true label is 1, binary cross-entropy generates a massive loss penalty and an immense gradient signal that aggressively forces the weights away from that confident mistake. When generalizing from binary classification to multi-class classification, where an input must be assigned to one of k mutually exclusive categories, we utilize categorical cross-entropy loss. In multi-class classification, the ground truth target is encoded as a one-hot vector, a vector of length k containing a 1 at the index corresponding to the true category and zeros at all other indices. The network's output layer uses a softmax activation function to output a vector of length k containing predicted probabilities that sum to 1.0. Categorical cross-entropy measures the cross-entropy between the true one-hot probability distribution and the predicted softmax probability distribution. Mathematically, it multiplies the true probability of each class by the negative natural logarithm of the predicted probability for that class, and sums the results across all categories. Because the true target vector is one-hot, containing zeros for every incorrect category and a 1 for the true category, all terms in the summation evaluate to 0 except for the single term corresponding to the true target class. Consequently, categorical cross-entropy simplifies to a remarkably concise expression. It is simply the negative natural logarithm of the predicted probability assigned to the true correct class. This concise simplification highlights why softmax and categorical cross-entropy form a tightly coupled computational pair. The softmax activation distributes probability mass across all candidate categories, while categorical cross-entropy penalizes any probability mass that was withheld from the single correct target class. To evaluate the mathematical relationship between different probability distributions, information theory provides a foundational metric called Kullback-Leibler divergence, universally known as KL divergence. KL divergence measures the relative entropy or information loss incurred when an approximating probability distribution is used to represent a true underlying probability distribution. It quantifies how much information is lost by substituting the approximation for the truth. In deep learning, KL divergence is deeply connected to cross-entropy loss. Mathematically, the cross-entropy between a true distribution and a predicted distribution equals the absolute entropy of the true distribution plus the KL divergence between them. Because the true ground truth labels in a dataset are fixed and unalterable, the entropy of the true distribution is a constant scalar. Therefore, minimizing categorical cross-entropy during network training is mathematically identical to minimizing the KL divergence between the predicted distribution and the true data distribution. While standard cross-entropy loss excels on balanced classification datasets, it suffers from a fatal limitation when applied to real-world tasks characterized by extreme class imbalance, such as detecting rare medical anomalies, automated fraud identification, or small object detection in aerial images. In an extreme class imbalance scenario, negative background samples might outnumber positive target samples by a ratio of 10,000 to 1. If you evaluate standard binary cross-entropy loss on a mini-batch containing 10,000 easy negative background samples and only one hard positive target sample, the collective accumulated loss from the 10,000 easy negatives, even if each individual negative error is tiny, completely dominates the total loss vector. The single hard positive samples gradient is drowned out by the flood of easy background gradients. The network quickly learns a degenerate strategy, predicting background for everything, achieving 99.9% accuracy while failing entirely to detect the rare targets. To solve this class imbalance bottleneck, researchers engineered focal loss. Focal loss modifies standard binary cross-entropy by introducing an adaptive modulating factor that dynamically downweights the loss assigned to easy, well-classified samples during training. Focal loss multiplies standard cross-entropy by a modulating term equal to 1 minus the predicted probability assigned to the true class, raised to a focusing hyperparameter power, typically denoted as gamma. To visualize how focal loss works, consider an easy negative sample that the network already classifies correctly with a high probability of 0.99. 1 minus 0.99 yields 0.01. If gamma is set to 2, squaring 0.01 shrinks the loss penalty for that easy sample by a factor of 10,000. Conversely, for a hard, misclassified positive sample where the predicted probability is only 0.1, 1 minus 0.1 yields 0.9. Squaring 0.9 preserves 81% of the sample's loss penalty. By exponentially suppressing the loss contributions from millions of easy background samples, focal loss ensures that the total mini-batch gradient is dominated entirely by the rare, hard target samples that actually require learning, enabling robust deep learning models to be trained successfully on extreme imbalanced data distributions. Finally, we must consider a distinct paradigm of loss function design known as metric learning or embedding loss, exemplified by triplet loss and contrastive loss. In tasks such as facial recognition, signature verification, or zero-shot image retrieval, the goal is not to classify an input into a fixed set of predefined categories, but to learn an embedding space where semantically similar items are mapped to nearby coordinates, while dissimilar items are mapped to distant coordinates. Triplet loss operates on triplets of samples evaluated simultaneously. An anchor sample, a positive sample belonging to the exact same identity as the anchor, and a negative sample belonging to a completely different identity. The network passes all three samples through its layers to extract their high-dimensional vector embeddings. Triplet loss then calculates two Euclidean distances: the distance between the anchor embedding and the positive embedding, and the distance between the anchor embedding and the negative embedding. The objective of triplet loss is to force the anchor positive distance to be smaller than the anchor negative distance by at least a specified safety margin hyperparameter. If the negative embedding is already far away from the anchor, further than the positive distance plus the safety margin, the triplet generates zero loss penalty. If the negative embedding is too close to the anchor, triplet loss generates a positive penalty proportional to the violation, forcing backpropagation to pull the positive embedding closer to the anchor while pushing the negative embedding further away. Having established how loss functions convert tasks into differentiable penalty surfaces, we must now examine how to prevent networks from memorizing training data through overfitting prevention techniques. A deep neural network possessing millions of trainable parameters possesses immense computational capacity. Given sufficient training iterations and a large parameter footprint, a deep network can easily memorize an entire training dataset by heart, fitting every noise fluctuation, measurement artifact, and label anomaly present in the training set. However, a model that merely memorizes its training data is completely useless in production because it fails to generalize to new, unseen real-world data samples. The central challenge in modern machine learning engineering is not merely minimizing training loss, but preventing overfitting and maximizing generalization performance. To build an intuitive mental model of overfitting prevention, we must examine the classic statistical concept known as the bias-variance trade-off. Bias refers to the error introduced by an overly simplistic model assumption. A model suffering from high bias, commonly known as underfitting, lacks the mathematical capacity or structural depth to capture the true underlying patterns in the data. For example, attempting to fit a complex curved boundary using a single linear decision hyperplane results in underfitting. An underfitting model exhibits high error rates on both the training dataset and the validation dataset. Variance, on the other hand, refers to the model's sensitivity to small fluctuations in the specific training dataset. A model suffering from high variance, known as overfitting, possesses excessive structural capacity relative to the dataset size. It carves out intricate, highly contorted decision boundaries around individual training points, memorizing specific noisy samples rather than learning generalizable principles. An overfitting model exhibits near-zero error on the training set, but suffers from a massive spike in error when evaluated on unseen validation data. The difference between training performance and validation performance is called the generalization gap. To close the generalization gap and prevent deep networks from memorizing training noise, software engineers deploy a suite of regularization techniques. Regularization encompasses any structural constraint, objective penalty, or stochastic modification applied to a learning system that explicitly restricts its capacity to memorize training data without reducing its ability to learn underlying patterns. The first major category of regularization is explicit parameter regularization, commonly implemented as L2 weight decay and L1 regularization. L2 weight decay, also known as ridge regularization, penalizes large parameter magnitudes by adding an explicit penalty term to the network's loss function. The L2 penalty equals 1/2 multiplied by a regularization hyperparameter, denoted as lambda, multiplied by the sum of squared weights across all layers in the network. To understand how L2 weight decay constrains parameter growth, examine its impact on the gradient update rule. During backpropagation, the derivative of the L2 penalty with respect to a weight equals lambda multiplied by the weight itself. When we combine this penalty derivative with the loss gradient, the weight update equation subtracts a fraction of the current weight magnitude directly from the weight. This parameter contraction means that during every single update step, the optimizer multiplies every weight in the network by a decay factor slightly less than 1.0, such as 0.99, before applying the standard gradient step. This constant multiplicative shrinking is why L2 regularization is universally called weight decay. Weight decay forces the network to distribute its decision logic across many small, balanced weights rather than relying on a small number of massive weights. When a network relies on massive weights, tiny fluctuations in incoming input features are amplified into huge shifts in activation values, making the model hypersensitive to input noise. By forcing weights to stay small, L2 decay smooths out the network's function surface, ensuring that small changes in input features produce small, controlled changes in output decisions. L1 regularization, also known as lasso regularization, penalizes the sum of absolute weight values rather than squared weights. The L1 penalty adds lambda multiplied by the sum of absolute weights to the loss function. The derivative of the absolute weight function is a constant value equal to positive lambda for positive weights and negative lambda for negative weights. Unlike L2 weight decay, where the decay force shrinks toward zero as the weight gets smaller, L1 regularization applies a constant, unyielding inward decay force regardless of how small the weight becomes. This constant inward decay force gives L1 regularization a unique property. It drives small, unimportant weights all the way to absolute zero, effectively turning off connections. As a result, L1 regularization produces sparse weight matrices where a large percentage of weights are exactly zero. Sparse weight matrices act as an implicit feature selection mechanism, pruning out irrelevant input features and creating highly compressed models. While parameter penalties penalize weight magnitudes explicitly, one of the most powerful and revolutionary regularization breakthroughs in deep learning is a stochastic technique called dropout. Dropout takes an entirely different approach to regularization. Instead of modifying the loss function, it introduces random noise directly into the network architecture during the forward pass of training. During each forward pass of training, Dropout randomly deactivates or drops out a subset of neurons in a layer with a specified probability, typically denoted as P, where P is commonly set between 0.2 and 0.5. When a neuron is dropped out for a specific mini-batch, its activation value is forcibly set to 0, and its connections are temporarily severed for both the forward pass and the subsequent backward pass. On the next mini-batch, a completely new, independently sampled mask of random neurons is dropped out. Across thousands of training steps, the network never sees the exact same architecture twice. To understand why dropout is extraordinarily effective at preventing overfitting, we evaluate two distinct mental models, eliminating coadaptation and implicit ensemble averaging. First, consider the problem of feature coadaptation. In unregularized deep networks, individual neurons frequently develop unhealthy dependencies on one another. A neuron in layer 2 might rely on a highly specific, fragile combination of outputs from 3 specific neurons in layer 1 to render a correct decision. If one of those layer 1 neurons receives a noisy input, the entire downstream decision fails. Dropout completely destroys coadaptation. Because any neuron can vanish at any instant with probability P, a downstream neuron cannot rely on the presence of any single upstream partner. It is forced to learn robust, independent feature representations that provide useful signal even when neighboring neurons are absent. Each neuron becomes a self-sufficient feature detector that collaborates effectively with arbitrary random subsets of peers. Second, consider the ensemble perspective. Training a network with Dropout is mathematically equivalent to training an ensemble collection of 2 to the power of n distinct, thin subnetworks, where n is the total number of neurons in the layer. All these subnetworks share parameter weights. Every mini-batch trains a different thin subnetwork on a different sample of data. When training is completed, we turn off Dropout for production inference. At test time, all neurons remain active simultaneously. Passing data through the full, undropped network at test time is mathematically equivalent to taking an approximate geometric average across the predictions of all 2 to the power of n subnetworks trained during learning. Ensemble averaging across thousands of diverse subnetworks dramatically reduces prediction variance and delivers pristine generalization performance. To ensure that test time predictions remain numerically accurate when Dropout is turned off, software engines implement inverted dropout scaling during training. If we drop out 50% of the neurons in a layer during training, the sum of incoming signals reaching the subsequent layer during training is reduced by half compared to when all neurons are active. If we simply turned off Dropout at test time without adjustments, the incoming signal amplitude would suddenly double, overwhelming the downstream activations. Inverted dropout resolves this scaling mismatch by dividing all active neuron outputs by 1 minus p during the forward pass of training. If p is 0.5, dividing active activations by 0.5 doubles their magnitude during training. This prescaling ensures that the expected total energy flowing into the subsequent layer during training matches the total energy received at test time when all neurons are active. By applying inverted dropout during training, test time inference requires zero modification or extra compute, running at full speed without scaling overhead. Alongside parameter penalties and dropout, the most widely used and intuitive regularization technique in deep learning pipelines is early stopping. Early stopping monitors the network's performance on an independent validation dataset throughout the training process. During the initial phase of training, both training loss and validation loss decrease synchronously as the network learns genuine, generalizable patterns from the data. However, as training continues past a certain threshold, the network exhausts the generalizable patterns and begins memorizing specific training noise. Early stopping automatically halts training when this inflection point is detected. In practice, software engines use a hyperparameter called patience. The patience hyperparameter defines how many consecutive training epochs the system will allow validation loss to deteriorate before triggering a hard stop. Using a patience window, such as 10 epochs, prevents the system from stopping prematurely due to temporary noise fluctuations or short plateaus in validation loss. Throughout training, the engine maintains a cached copy of the parameter weights that achieved the absolute lowest validation loss observed so far. When the patience counter expires, training terminates, and the engine restores the cached best weights, guaranteeing that the final deployed model captures peak generalization performance before overfitting occurred. Finally, we must examine data augmentation, which combats overfitting by expanding the effective size and diversity of the training dataset without collecting new raw samples. Overfitting occurs when the network possesses too much parameter capacity relative to the number of unique training samples available. If you cannot reduce network capacity or collect new data, data augmentation artificially synthesizes new training samples by applying domain-preserving transformations to existing data. In computer vision pipelines, data augmentation applies spatial and photometric transformations, such as random horizontal flips, subtle rotations, random cropping, color jittering, and affine warping to input images. Crucially, These transformations preserve the semantic identity of the label. A picture of a cat remains a cat whether it is flipped horizontally or slightly rotated. By feeding the network slightly different augmented variations of every image during every epoch, the network never sees the exact same raw pixel array twice. Data augmentation forces the model to learn invariant representations, learning that an object's identity does not depend on absolute pixel coordinates, lighting shifts, or orientation. In natural language processing, data augmentation techniques include random word insertion, synonym substitution, and backtranslation, where text is translated into a secondary language and back into the primary language to generate paraphrased training samples. Additionally, engineers inject small Gaussian noise into input features or intermediate hidden activations during training. Noise injection smooths out decision boundaries, forcing the network to become resilient against small input perturbations, further tightening the generalization gap. Having mastered overfitting prevention and regularization, we are now ready to analyze how these theoretical components synthesize into a concrete implementation from scratch using NumPy. To transition our understanding of neural networks from theoretical calculus to functional software systems, we must examine how to construct a complete multi-layer feedforward engine from scratch using raw numerical array operations in NumPy. Implementing a neural network from scratch without relying on high-level frameworks like PyTorch or TensorFlow is the ultimate test of engineering mastery. It strips away high-level abstractions, forcing us to manage tensor dimensions, memory allocations, forward pass caching, backpropagation derivatives, and numerical stability safeguards directly. To guide this implementation verbally, we will analyze the software architecture of a two-layer neural network designed for classification. Our engine consists of 4 primary modular components: parameter initialization, forward propagation with activation caching, backward propagation gradient computation, and optimization weight updating. The first architectural phase is parameter initialization. In NumPy, weight parameters are stored as two-dimensional floating point arrays, while biases are stored as two-dimensional horizontal row vectors. When defining array shapes, we establish a strict matrix convention. Rows represent incoming feature dimensions, while columns represent individual neurons in the layer. If our input dataset contains 784 features per sample, such as flattened 28 by 28 pixel images, and our first hidden layer contains 128 neurons, the first weight matrix is initialized with a shape of 784 rows by 128 columns. If the subsequent output layer contains 10 neurons for multi-class classification, the second weight matrix is initialized with a shape of 128 rows by 10 columns. The first bias vector is allocated as a 1 by 128 horizontal vector initialized to zeros, while the second bias vector is allocated as a 1 by 10 horizontal vector initialized to zeros. Initializing weight matrices requires careful mathematical scaling rather than setting all entries to 0. If you initialize all weights to 0 in NumPy, every neuron in a layer computes the exact same weighted sum, receives the exact same activation, and computes the exact same gradient during backpropagation. The neurons react symmetrically, updating their weights by identical amounts. This mathematical phenomenon, known as the symmetry constraint, prevents the network from learning distinct features, reducing 100 parallel neurons to a single redundant unit. To break symmetry, we populate weight matrices with small random numbers drawn from a Gaussian distribution. However, raw random numbers are insufficient for deep networks. If the variance of initial weights is set too large, Weighted sums explode as signals pass through layers, saturating activations. If initial variance is set too small, signals decay to zero. To maintain stable variance across layers, we scale the random Gaussian array by specific scaling formulas based on the activation function used. For layers utilizing ReLU activations, we multiply the random array by the square root of 2 divided by the number of incoming input nodes, a technique known as He or Kaming initialization. For layers utilizing tan or sigmoid activations, we scale by the square root of 1 divided by the incoming input nodes, known as Xavier or Glorot initialization. Proper variance scaling ensures that forward activation signals and backward gradient signals maintain consistent, non-exploding, non-vanishing amplitudes across all layers from the very first step. Once parameters are initialized, we implement the forward propagation function. The forward pass accepts a mini-batch feature array where rows represent individual training samples and columns represent features. If a mini-batch contains 64 samples, the input array has a shape of 64 rows by 784 columns. The first step of forward propagation computes the pre-activation matrix for the hidden layer using NumPy's .product function, multiplying the 64 by 784 input array by the 784 by 128 weight matrix yields a 64 by 128 matrix. We then add the 1 by 128 bias vector. NumPy automatically broadcasts the single bias row across all 64 sample rows, adding the bias offsets in parallel. Next, we pass this pre-activation matrix through our chosen nonlinear activation function. For a ReLU hidden layer, we apply NumPy's element-wise maximum function, comparing every entry in the matrix against 0. Any negative entry is replaced with 0, while positive entries remain unchanged. This yields the hidden post-activation matrix of shape 64 by 128. We then repeat this process for the output layer, multiplying the 64 by 128 hidden activation matrix by the 128 by 10 output weight matrix and adding the 1 by 10 bias vector produces the output pre-activation matrix of shape 64 by 10. To convert these output pre-activation logits into normalized probabilities for multi-class classification, we apply a numerically stabilized softmax function. To prevent floating point overflow during exponentiation, we compute the maximum logit value along each sample row using NumPy's keepDimensions max function and subtract this row-wise maximum from every logit in the row. We then exponentiate the adjusted logits using NumPy's exponential function and divide each exponentiated entry by the row-wise sum of exponentiated values. The result is our final predicted probability matrix of shape 64 by 10, where every row sums to exactly 1.0. Crucially, before exiting the forward propagation function, we store all intermediate arrays: the input array, the hidden pre-activation array, the hidden post-activation array, the output pre-activation array, and the predicted probability array, inside a dictionary data structure called the forward cache. Preserving these exact array references in memory is mandatory because they supply the exact activation values required to calculate local derivatives during backpropagation. We now enter the third phase, implementing backward propagation. The backward pass function retrieves the cached forward arrays and computes exact analytical gradients for all weight matrices and bias vectors using vectorized matrix operations. The backward pass begins at the output layer by evaluating the error delta of the loss function with respect to the output logits. For categorical cross-entropy loss paired with a softmax output layer, the derivative simplifies to a remarkably clean array operation, we take the predicted probability matrix and subtract the one-hot target label matrix. If a mini-batch contains 64 samples, subtracting the one-hot label array from the predicted probability array produces an output delta matrix of shape 64 by 10, representing the net prediction error for every sample in class. We then use this output delta matrix to calculate parameter gradients for the output layer. To find the gradient matrix for the output weights, we multiply the transpose of the hidden post-activation matrix, which has a shape of 128 rows by 64 columns, by the 64 by 10 output delta matrix, and divide the result by 64, the mini-batch size. The resulting array has a shape of 128 rows by 10 columns, matching the exact shape of the output weight matrix. Simultaneously, we calculate the output bias gradient array by summing the output delta matrix along its vertical column axis using NumPy's sum function across axis 0, keeping dimensions aligned, and dividing by the batch size. This yields a 1 by 10 row vector matching the output bias shape. Next, we propagate the error delta backward into the hidden layer. To transmit error signals through the output weight matrix, we multiply the 64 by 10 output delta matrix by the transpose of the 10 by 128 output weight matrix, yielding a 64 by 128 matrix of backprojected errors. To pass this backprojected error backward through the hidden layer's ReLU activation function, we perform an element-wise multiplication with the Boolean derivative mask of the hidden preactivation array. In NumPy, evaluating whether the cached hidden preactivation array is greater than 0 creates a Boolean array of true and false flags. We multiply the backprojected error matrix by this Boolean array, converting true flags to 1.0 and false flags to 0.0. This element-wise multiplication zeroes out error signals for any hidden neuron that was inactive during the forward pass, yielding the hidden layer delta matrix of shape 64 by 128. Finally, we calculate the parameter gradients for the hidden layer. We multiply the transpose of the 64 by 784 input matrix by the 64 by 128 hidden delta matrix, and divide by 64. This produces a 784 by 128 gradient matrix for the hidden weights. We sum the hidden delta matrix along axis 0 and divide by 64 to obtain the 1 by 128 gradient vector for the hidden bias. The backward pass returns all 4 gradient arrays in a structured dictionary. The final modular component is the optimization update function. The update function takes the parameter dictionary, the gradient dictionary, and a scalar learning rate. Using NumPy's in-place subtraction operations, it updates each weight matrix by subtracting the learning rate multiplied by its corresponding gradient array, and updates each bias vector by subtracting the learning rate multiplied by its bias gradient array. To verify that our NumPy backpropagation engine is completely free of mathematical bugs before executing long training runs, software engineers implement an essential debugging technique called gradient checking. Gradient checking verifies analytical backpropagation gradients against empirical numerical approximations. To perform gradient checking, we pick a small sample of data and iterate through every parameter in the network one by one. For a specific weight parameter, we add a tiny numerical delta, such as 10 to the power of -7, to the weight, run a complete forward pass, and record the scalar loss. We then reset the weight, subtract the tiny delta from the weight, run another forward pass, and record the scalar loss. By subtracting the second loss from the first loss and dividing by twice the delta value, we compute the centered finite difference numerical approximation of the derivative for that specific weight. We then compare this numerical approximation against the analytical gradient calculated for that exact weight by our backpropagation function. If our backpropagation math and array transpositions are coded correctly, the relative vector difference between the analytical gradients and the numerical approximations will be less than 10 to the power of -7 across all parameters. If the relative difference exceeds 10 to the power of -3, a mathematical or indexing bug exists in the backpropagation implementation, such as a misplaced matrix transpose, a missed activation derivative, or an incorrect batch division, alerting us to debug the engine before training. While building a neural network engine from scratch in NumPy provides deep foundational mastery, writing custom raw C or NumPy code for complex modern architectures containing hundreds of specialized layers is computationally inefficient and labor-intensive. In industry and production environments, developers rely on high-level deep learning frameworks like PyTorch and TensorFlow, which automate computational graph construction, automatic differentiation, GPU hardware acceleration, and distributed execution. In modern software engineering, raw numerical array frameworks like NumPy serve as exceptional educational tools, but building scalable production-grade deep learning applications requires high-level industrial frameworks. The modern machine learning ecosystem is dominated by two primary framework engines, PyTorch and TensorFlow, paired with its high-level interface, Keras. Both frameworks provide powerful abstractions for tensor operations, automatic differentiation engines, accelerator hardware management, and production deployment utilities. However, they embody fundamentally different design philosophies, computational graph execution models, and architectural paradigms. To evaluate these frameworks effectively, we must examine the core architectural divergence between dynamic computational graphs and static computational graphs. PyTorch operates primarily on a dynamic computational graph paradigm, often described as defined by run. In PyTorch, tensor operations execute imperatively line by line in real time, exactly like standard Python code. When you write a line of PyTorch code that multiplies two tensors together, the framework executes the underlying C++ or CUDA kernel immediately and returns the resulting tensor value instantly. As data flows forward through a PyTorch model during the forward pass, PyTorch's automatic differentiation engine, called AutoGrad, dynamically constructs a temporary computational graph in memory on the fly. Every tensor initialized with gradient tracking enabled acts as a node in this dynamic graph, recording the specific mathematical operations that created it alongside references to its parent tensors. This define by run philosophy provides immense software engineering flexibility. Because the computational graph is constructed dynamically during execution, you can incorporate standard Python control flow logic, such as conditional if statements, while loops, or variable length sequence iterations, directly inside the forward pass of your neural network. If you want a network to route signals through different hidden layers based on an input feature value, PyTorch handles this conditional routing natively without special graph compilation wrappers. Furthermore, imperative execution makes debugging exceptionally intuitive. Software engineers can insert standard Python breakpoints, inspect intermediate tensor shapes and values using standard debuggers, and print gradient values at any point in the code without breaking the framework. Conversely, TensorFlow was historically built upon a static computational graph paradigm, known as define and run, which has evolved into a hybrid execution engine powered by symbolic graph compilation tools such as that tf.function and the accelerated linear algebra compiler, known as XLA. In a static graph paradigm, model definition is completely decoupled from model execution. First, the software engineer defines the symbolic structure of the entire neural network, specifying every layer, activation, and tensor shape, building an abstract mathematical graph blueprint in memory. Second, The framework passes this complete static graph blueprint to a specialized graph compiler engine. The graph compiler analyzes the entire computational network holistically before a single data sample is processed. It performs aggressive low-level compiler optimizations, fusing adjacent mathematical operations into single GPU kernels, eliminating redundant intermediate tensor allocations, reordering operations to maximize memory bandwidth, and pre-allocating fixed memory buffers on target hardware accelerators. Once compiled, the static graph executes at blazing speeds with minimal Python runtime overhead. To bridge the gap between PyTorch's developer-friendly imperative flexibility and TensorFlow's high-throughput graph performance, modern versions of both frameworks support hybrid execution modes. PyTorch incorporates graph compilation tools that trace imperative Python code into static graphs for production deployment, while TensorFlow defaults to imperative eager execution for development while allowing selective graph compilation for performance-critical modules. To organize complex neural network code cleanly, both frameworks provide high-level object-oriented modular abstractions. In PyTorch, custom neural network architectures are constructed by subclassing the core module class, named NN. Module. A PyTorch module follows a strict, elegant design pattern. In the class initialization constructor method, you instantiate and register all parameter-bearing layers, such as dense linear layers, convolutional layers, or normalization layers, as internal member attributes. You then override the mandatory forward method, which defines the exact forward computational paths of the network. The forward method accepts input tensors, passes them sequentially through the instantiated layers and activation functions, and returns the output predictions. Crucially, you never write explicit code for the backward pass in PyTorch. When you call the backward method on the final scalar loss tensor returned by your model, PyTorch's AutoGrad engine automatically traverses the dynamic computational graph constructed during the forward pass in reverse, computing exact analytical gradients for all registered parameters in the module and storing them inside each parameter's gradient attribute. In TensorFlow and Keras, model building offers three distinct architectural approaches: the sequential API, the functional API, and model subclassing. The Keras sequential API provides an extremely concise interface for simple architectures where layers are stacked in a single linear chain without branch connections or multiple inputs. You simply instantiate a sequential object and pass an ordered list of layer instances. For architectures featuring complex topological structures, such as multi-input models, multi-output heads, residual skip connections, or shared layer weights, developers utilize the Keras functional API. The functional API treats layers as callable functions operating on symbolic tensors, allowing engineers to build directed acyclic graphs by explicitly passing tensor variables from layer function to layer function. For complete architectural freedom matching PyTorch's paradigm, developers subclass the tf.keras model class, instantiating layers in the constructor and defining custom forward computation logic inside the call method. Beyond model definition, a critical engineering responsibility of modern frameworks is hardware acceleration management across CPUs, GPUs, and TPUs. A central processing unit, or CPU, is engineered for low-latency sequential execution, featuring a small number of powerful processor cores paired with large cache memories optimized for complex branching logic. A graphics processing unit, or GPU, is engineered for high-throughput parallel execution, featuring thousands of simpler processor cores optimized for simultaneous floating-point matrix arithmetic. A tensor processing unit, or TPU, is a specialized application-specific integrated circuit custom-built exclusively for massive matrix multiplication workloads. To leverage hardware accelerators, deep learning frameworks manage asynchronous execution engines and memory transfers between host system RAM and accelerator VRAM. When executing code on a GPU, tensor data must reside directly within the GPU's dedicated high-speed VRAM memory. In PyTorch, moving a tensor or model from system CPU memory to GPU VRAM requires calling the explicit target device method, passing a device string specifying CUDA execution. In TensorFlow, device placement is managed automatically by the runtime engine or explicitly scoped using device context managers. However, moving tensor data between host CPU memory and GPU VRAM across the PCI Express bus is a computationally slow operation that introduces severe latency bottlenecks. If a training pipeline reads raw data from disk into CPU memory, preprocesses it on the CPU, and transfers it sample by sample to the GPU during every step, the GPU processor cores spend 80% of their time sitting idle, waiting for memory transfers across the bus. This state is known as an input-bound or I/O-bound training pipeline. To eliminate data transfer bottlenecks and keep hardware accelerators operating at 100% utilization, modern frameworks provide specialized, multi-threaded data loading pipelines. In PyTorch, data loading is governed by two complementary classes: the dataset class and the data loader class. The dataset class defines how to fetch and preprocess a single sample from disk or storage. The data loader class wraps around the dataset object, managing parallel mini-batch creation, asynchronous background prefetching, memory locking, and multi-process data loading. The data loader spawns multiple parallel background worker processes on the CPU. While the GPU is actively processing the current mini-batch, these background CPU workers asynchronously load, decode, augment, and batch the subsequent 3 or 4 mini-batches in CPU memory ahead of time. Furthermore, by enabling memory pinning, often called pinned memory, the data loader allocates the prefetched mini-batches inside page-locked CPU host memory. Page-locked memory allows the host system to initiate direct memory access transfers directly to GPU VRAM without involving CPU kernel overhead. Consequently, when the GPU finishes its current compute step, the next mini-batch is already staged in pinned memory and transfers instantly to VRAM over the bus, completely hiding data loading latency. Similarly, TensorFlow provides the powerful tf.data API, which models data pipelines as declarative ETL chains, extract, transform, and load. Using tf.data, developers construct declarative pipelines by chaining transformation methods such as map, filter, batch, interleave, and prefetch. The tf.data prefetch transformation automatically overlaps the execution of data preprocessing with model training steps. By specifying an auto-tuned prefetch buffer size, the framework dynamically adjusts the background prefetch pipeline based on real-time hardware performance, ensuring zero GPU idle time. Finally, we must evaluate hardware execution limits. The distinction between memory-bound operations and compute-bound operations. Compute-bound operations are tasks where execution speed is limited strictly by the processor's floating-point calculation capacity, measured in flops. Large, dense matrix multiplications and convolutions are compute-bound. They perform many mathematical operations per byte of data loaded from memory, fully utilizing GPU arithmetic cores. Memory-bound operations are tasks where execution speed is limited by memory bandwidth, the rate at which data can be read from or written to VRAM. Element-wise operations, such as activation functions, bias additions, layer normalizations, and dropout masks, are memory-bound. They perform very few arithmetic calculations per byte, spending most of their execution time waiting for memory buses to fetch tensor entries from VRAM into register cache. Modern framework engines optimize memory-bound operations using kernel fusion. Kernel fusion takes multiple sequential element-wise operations, such as a bias addition followed by a ReLU activation and a dropout mask, and compiles them into a single unified GPU kernel execution. Instead of writing intermediate results back to VRAM after each operation and reading them back for the next, fused kernels keep intermediate values inside superfast GPU register memory, executing the entire sequence in a single pass and increasing training throughput by up to 40%. Having mastered the architectural paradigms and hardware execution mechanics of PyTorch and TensorFlow, we now examine training dynamics, debugging, and hyperparameter tuning. Training deep neural networks in production is rarely a seamless, single-step process. In practice, deep architectures exhibit complex, nonlinear training dynamics that require systematic monitoring, empirical debugging, and rigorous hyperparameter tuning. An improperly initialized network can suffer from exploding gradients within 3 steps, while an untuned learning rate schedule can cause a model to stall indefinitely in a suboptimal saddle point. To operate like an elite system architect, you must master the mechanics of weight initialization, gradient stabilization, learning rate scheduling, loss curve diagnosis, and automated hyperparameter search. We begin our analysis with weight initialization strategies, which establish the initial signal variance across deep computational graphs. When a neural network begins training, its parameter weights must be initialized to small random values to break symmetry. However, selecting the precise variance scale for those random values governs whether forward activations and backward gradients maintain stable numerical magnitudes or disintegrate into vanishing or exploding extremes. Consider what occurs during the forward pass if we initialize weights with excessive variance. In a dense layer, each neuron computes a weighted sum over many input nodes. If the input variance is multiplied by large weight variances across 50 stacked layers, the variance of activation signals expands exponentially with depth. By the time signals reach deeper layers, pre-activation values reach massive magnitudes, saturating nonlinear activation functions, driving derivatives to 0, and causing forward activations to explode to infinity. Conversely, if we initialize weights with microscopic variance near 0, activation variance shrinks exponentially with depth. By the time signals reach deeper layers, all activation values collapse to absolute 0, causing the network to lose all representation capacity. To preserve constant activation variance forward and constant gradient variance backward across stacked layers, mathematicians engineered mathematically rigorous initialization formulas based on layer fan-in and fan-out, where fan-in represents the number of incoming input connections, and fan-out represents the number of outgoing connections. For symmetric, saturating activation functions such as tan and sigmoid, the standard technique is Xavier or Glorot initialization. Xavier initialization sets the variance of initial weights equal to 2 divided by the sum of fan-in plus fan-out. By scaling initial weight variance inversely with the average layer width, Xavier initialization guarantees that the variance of a layer's output activations equals the variance of its input activations, preventing signal collapse or explosion across symmetric layers. However, when deep networks transition to non-symmetric, rectified activations like ReLU, Xavier initialization failed. Because ReLU zeroes out the entire negative half of its input domain, it effectively cuts activation variance in half at every layer. Passing signals through a chain of ReLU layers using Xavier initialization causes activation variance to decay by 50% per layer, leading to vanishing signals in deep architectures. To fix variance decay in rectified networks, He or K-means initialization was developed. K-means initialization accounts explicitly for ReLU's half-space zeroing by setting initial weight variance equal to 2 divided strictly by fan-in. Multiplying by 2 restores the lost variance, ensuring pristine, constant signal amplitude forward and backward across hundreds of stacked ReLU layers. Even with pristine initialization, deep networks can experience temporary numerical instability during training, manifested as exploding gradients. Exploding gradients occur when backward error signals multiply across deep layers or unrolled recurrent steps, accumulating into massive gradient magnitudes. When an optimizer encounters an exploding gradient vector, taking a parameter step multiplied by a large gradient produces a violent, destabilizing leap in parameter space. The parameters jump far away from valid loss regions into numerical saturation zones, causing the training loss to instantly jump from a healthy value to not a number overflow, crashing training. To protect deep networks against gradient explosion, software engines implement gradient clipping. Gradient clipping acts as a numerical safety governor, enforcing an absolute ceiling on gradient step sizes. There are 2 primary methods of gradient clipping: value clipping and norm clipping. Value clipping inspects every individual element within a gradient tensor independently and clamps its scalar value to reside strictly within a specified numerical interval, such as -1.0 to +1.0. Any gradient component exceeding +1 is forced to +1, and any component below -1 is forced to -1. However, value clipping distorts the directional orientation of the gradient vector. To preserve directional orientation while preventing gradient explosion, modern pipelines utilize norm clipping. Norm clipping calculates the global L2 vector norm across all parameter gradients in the network, representing the total magnitude of the combined gradient vector. If the global L2 norm is less than or equal to a specified maximum threshold hyperparameter, such as 1.0, the gradient vector remains completely untouched. However, if the global norm exceeds the maximum threshold, the algorithm scales the entire gradient vector down by multiplying every element by the threshold divided by the global norm. Norm clipping preserves the exact geometric angle and directional orientation of the gradient vector perfectly, but caps its total physical step length at the maximum threshold. If a sudden catastrophic gradient spike occurs during a noisy batch, norm clipping shrinks its length to a safe, controlled magnitude, allowing the optimizer to navigate steep cliffs smoothly without blowing up parameter weights. Alongside gradient clipping, managing learning rate dynamics over time using learning rate schedules and warm-up strategies is critical for reaching optimal convergence. Fixed learning rates are rarely optimal throughout an entire training run. Early in training, when parameter weights are randomly initialized, the network benefits from a larger learning rate to make rapid progress across high-altitude loss regions. Late in training, when parameters are close to a narrow optimal minimum, a large learning rate causes the optimizer to overshoot the valley floor, requiring a much smaller learning rate to settle into exact optimal coordinates. To adapt the learning rate over time, engineers deploy automated learning rate decay schedules. A common schedule is exponential decay or step decay, which multiplies the learning rate by a decay factor, such as 0.9 every fixed number of epochs or steps. A more sophisticated and widely adopted schedule in modern deep learning is cosine annealing. Cosine annealing smoothly decays the learning rate from a maximum initial value down to a microscopic minimum value following a cosine curve over the total scheduled training steps. The smooth, continuous curvature of cosine annealing provides an ideal learning trajectory. It maintains a relatively high learning rate during early epochs for rapid exploration, transitions into a steep smooth decay during mid-training, and flattens out near zero during final epochs, allowing the model to settle into the deepest region of the local minimum. To complement decay schedules, modern pipelines almost universally incorporate learning rate warm-up. During the initial steps of training, when weights are randomly initialized or when fine-tuning a pre-trained model on new data, the initial loss gradients computed across early mini-batches are extremely large and noisy. If you apply a large maximum learning rate during these very first steps, large noisy gradients can permanently destroy beneficial weight structures or destabilize the optimizer's moment accumulators. Learning rate warm-up resolves initial instability by starting training with a tiny learning rate near zero and linearly increasing the learning rate step by step over a specified warm-up window, such as 2000 steps, until it reaches the target maximum learning rate. Warm-up acts as a gentle stabilization period. It allows the network's internal activations, batch normalization statistics, and optimizer moment accumulators to settle into coherent, stable states before subjecting the parameters to full magnitude learning rate updates. To diagnose training failures effectively in production environments, software engineers analyze the real-time telemetry of training and validation loss curves. Loss curve analysis provides an empirical window into the internal training dynamics of the model. Consider the first primary diagnostic pattern, underfitting. If both the training loss curve and the validation loss curve flatten out early and stall at unacceptably high error values, the model is underfitting. Underfitting indicates that the network lacks the capacity to represent the data distribution, or that optimization is blocked. To resolve underfitting, system architects increase network capacity by adding deeper layers or wider hidden channels, decrease regularization penalties by reducing dropout or weight decay, increase the learning rate, or verify that input features are properly scaled and normalized. Consider the second diagnostic pattern, overfitting. If the training loss curve continues to decrease smoothly towards zero, but the validation loss curve reaches a minimum and then begins to diverge upward, creating a widening generalization gap, the model is overfitting. To resolve overfitting, architects increase regularization penalties, raising dropout rates, increasing L2 weight decay, introducing data augmentation pipelines, incorporating early stopping, or collecting additional raw training samples. Consider the third diagnostic pattern, training instability and oscillations. If the loss curve exhibits violent, erratic spikes, jumping up and down wildly between steps, or if the loss suddenly evaluates to not a number, training is numerically unstable. To resolve numerical instability, engineers inspect the pipeline for unclipped gradients, lower the peak learning rate, extend the learning rate warm-up window, verify that softmax operations use logsum-exp numerical stabilization, and audit input feature datasets for corrupted zero values or infinite outliers. Finally, to discover optimal combinations of architectural choices and optimization parameters, machine learning engineers execute systematic hyperparameter search strategies. Hyperparameters such as learning rate, batch size, weight decay coefficient, dropout probability, layer width, and network depth cannot be learned directly via backpropagation. They govern the learning process itself, requiring systematic external search frameworks. The simplest search strategy is grid search. Grid search defines a fixed, discrete grid of candidate values for each hyperparameter and evaluates every possible Cartesian product combination exhaustively. While grid search is intuitive, it suffers severely from the curse of dimensionality. If you evaluate 5 candidate values across 6 distinct hyperparameters, grid search requires training 5 to the power of 6, 15,625, complete neural network models, making it computationally prohibitive for deep architectures. Furthermore, grid search wastes compute because hyperparameter dimensions do not contribute equally to performance. Evaluating fine grid steps along an unimportant hyperparameter yields zero insight. To overcome the inefficiency of grid search, engineers rely on random search. Random search samples hyperparameter combinations randomly from continuous probability distributions across the search space. Empirical research proves that random search is vastly superior to grid search for high-dimensional hyperparameter optimization. Because different hyperparameters drive model performance to varying degrees, random search evaluates unique, distinct values along every single hyperparameter dimension in every trial, exploring high-impact parameter spaces far more efficiently with a fraction of the compute budget. For state-of-the-art hyperparameter optimization, industry frameworks utilize Bayesian optimization, such as tree-structured Parson estimators or TPE. Bayesian optimization treats hyperparameter search as a sequential decision-making problem under uncertainty. Instead of sampling trial points purely at random, Bayesian optimization constructs an internal probabilistic surrogate model, such as a Gaussian process, that estimates the expected model performance across the hyperparameter space based on past trial results. Using an acquisition function that balances exploration of unknown regions with exploitation of highly performing regions, Bayesian optimization intelligently selects the single most promising hyperparameter combination to evaluate in the next trial. By continuously updating its surrogate model after every trial, Bayesian optimization converges on optimal hyperparameter configurations using a small fraction of the trials required by grid or random search. Beyond basic feature scaling at the input layer, maintaining stable internal activation distributions throughout deep architectures requires specialized internal normalization layers. As signals cascade forward through dozens of parameter updates, the distribution of activations at deeper layers shifts continuously throughout training, a phenomenon historically termed internal covariate shift. To stabilize deep activation distributions, architects deploy 4 distinct normalization paradigms: batch normalization, layer normalization, instance normalization, and group normalization. To build a unified mental model of normalization layers, visualize a 3-dimensional tensor of activations produced by a hidden layer, where the 3 axes represent the batch dimension, the feature or channel dimension, and the spatial or sequence dimension. The fundamental difference between normalization layers lies entirely in which axes they aggregate over to compute mean and variance statistics. We re-examine batch normalization first. Batch normalization computes mean and variance statistics across the batch dimension and spatial dimensions, independently for each feature channel. For a given feature channel, normalization gathers activation values across all samples in the mini-batch, computes their mean and variance, subtracts the mean, and divides by the standard deviation. It then applies 2 learnable parameters, gamma for scaling and beta for shifting, restoring model capacity. Batch normalization delivers remarkable empirical benefits. It smooths the loss landscape, prevents vanishing and exploding gradients, and acts as a mild stochastic regularizer due to mini-batch variance noise. However, batch normalization suffers from three severe operational limitations. First, batch normalization is highly dependent on mini-batch size. If the mini-batch size is too small, such as 2 or 4 samples per GPU during large image or sequence training, the empirical mean and variance computed over those few samples are extremely noisy and inaccurate, causing training performance to plummet. Third, batch normalization fails on variable-length sequential data, such as natural language text, because sequence lengths vary across batch samples, making batch-wide channel statistics unstable. To eliminate dependence on mini-batch size and handle sequential data natively, layer normalization was engineered. Layer normalization flips the aggregation axis. Instead of computing statistics across the batch dimension for each channel independently, layer normalization computes mean and variance statistics across all feature channels independently for each individual sample in the batch. Because layer normalization operates strictly within a single data sample, its normalization calculations are completely independent of mini-batch size. Whether the mini-batch contains 1 sample or 1,000 samples, layer normalization computes the exact same mean and variance for a given sample. Furthermore, layer normalization behaves identically during training and inference, eliminating the need for running statistical accumulators. Consequently, layer normalization has become the universal standard normalization layer for sequence architectures, transformers, and large language models. To complete the normalization matrix, we evaluate instance normalization and group normalization. Instance normalization computes mean and variance statistics across spatial dimensions independently for each single sample and each single channel. Instance normalization strips out style, contrast, and global intensity variations from individual features, making it the preferred normalization technique for style transfer and image generation networks. Group normalization provides a flexible middle ground between layer normalization and instance normalization. Group normalization divides the feature channels into small groups, such as 32 channels per group, and computes mean and variance statistics across the channels within each group independently for each sample. Group normalization remains completely independent of batch size while retaining spatial channel relationships, making it the ideal normalization layer for high-resolution visual tasks, where small batch sizes are enforced by GPU VRAM limits. Having mastered training dynamics, numerical stabilization, loss curve debugging, and hyperparameter tuning, we now synthesize all these engineering concepts into an end-to-end practical neural network project. To synthesize every fundamental concept, mathematical mechanism, and optimization strategy we have mastered throughout this lesson, we now execute an end-to-end practical system design project. We will step into the shoes of a principal machine learning system architect tasked with designing, building, validating, and deploying a production-grade deep neural network system engineered to solve a complex, multimodal enterprise prediction problem. By walking through this practical engineering project step by step, from initial problem formulation and data pipeline design, through architectural topology selection and distributed training, to model diagnostics, quantization, and real-time production deployment, you will gain a comprehensive mental model of how deep learning systems operate in real-world industrial environments. We begin with Phase 1, end-to-end problem formulation and system context. In modern enterprise applications, machine learning systems rarely perform isolated single-variable predictions. Consider a real-world financial technology platform processing millions of transaction events per second. The business requires a centralized intelligent engine that performs multitask evaluation in real time, predicting whether an incoming transaction is fraudulent, estimating the long-term continuous credit risk score of the user, and categorizing the transaction into one of several merchant risk categories. To solve this multifaceted business goal, we formulate our machine learning task as a multitask learning neural network. Instead of building and deploying 3 separate machine learning models, which would triple infrastructure costs, increase inference latency, and duplicate data processing pipelines, we design a single unified neural network featuring a shared deep feature extraction backbone connected to 3 specialized task output heads. The first output head performs binary classification for fraud detection, using a single output neuron paired with a sigmoid activation function to produce a calibrated fraud probability between 0 and 1. The second output head performs continuous scalar regression for risk estimation, using a single linear output neuron to produce an unbounded real-valued risk score. The third output head performs multi-class categorization for transaction risk grading, using a vector of output neurons paired with a softmax activation function to produce a joint probability distribution across risk categories. Formulating the system as a multitask network delivers a profound architectural advantage known as inductive bias sharing. As raw feature signals pass through the shared feature extraction backbone, the network is forced to learn internal representations that satisfy all 3 tasks simultaneously. Features learned to assist transaction risk grading help regularize the fraud detection head, while representation signals from continuous credit risk estimation prevent the categorical head from overfitting. Shared representation learning improves sample efficiency and generalization across all tasks. Having established our multitask problem formulation, we move to Phase 2, data pipeline architecture, pre-processing, and leakage prevention. Raw enterprise data ingested from production databases is messy, heterogeneous, unnormalized, and filled with missing entries. Raw data cannot be fed directly into a neural network. Neural networks process floating-point tensors, and their gradient descent optimization engines depend heavily on input feature scaling and geometric alignment. The first critical engineering mandate in data pipeline design is strict data leakage prevention during dataset splitting. Data leakage occurs when information from the validation dataset or test dataset inadvertently leaks into the training pipeline during pre-processing, creating artificially inflated evaluation metrics that plummet when the model is deployed to production. To prevent data leakage, we partition our raw historical data into 3 distinct subsets: a training set, a validation set, and a test set. If our data possesses temporal dependencies, such as transaction sequences over time, we must never use simple random splitting. Random splitting samples historical transactions randomly across time, allowing the training set to observe future transactions while predicting past events, severely contaminating the validation metrics. Instead, we enforce a strict time-based split. The training set contains all transactions up to a specific historical cutoff timestamp. The validation set contains transactions from the subsequent time window, and the test set contains the most recent production window. Furthermore, if transactions belong to specific user accounts, we enforce a group-based split, ensuring that all transactions from any single user reside exclusively within one dataset split, preventing the model from memorizing user-specific identities. Once data is cleanly partitioned, we fit all data pre-processing transformations strictly on the training set alone, and apply those fitted transformation parameters to the validation and test sets without refitting. Pre-processing tabular input features involves distinct transformations for continuous numerical variables and discrete categorical variables. For continuous numerical features, such as transaction amount, account age, or historical balance, we apply a combination of nonlinear transformations and standard feature scaling. Continuous features in financial domains frequently exhibit heavily skewed, long-tailed distributions, where 99% of values are small, but rare transactions reach millions of dollars. If fed raw, large skewed inputs dominate weighted sums and destabilize gradients. To compress long-tailed distributions, we first apply a logarithmic transform, specifically taking the natural logarithm of 1 plus the feature value. The log transform squashes extreme positive values, bringing skewed distributions back into approximately Gaussian bell curve shapes. Next, we apply standard scalar normalization. Standard scalar calculates the empirical mean and standard deviation of each feature across the training set, subtracts the mean from each feature value, and divides by the standard deviation. This transformation centers continuous features around 0 with a unit variance of 1.0. Centering features around 0 ensures that gradient steps during early training propagate smoothly without directional bias. For discrete categorical features, such as transaction country, device type, or merchant category, we must convert text labels into numerical representations suitable for neural networks. For low cardinality categorical features containing only a few unique values, such as device type, we apply one-hot encoding, converting each category into a binary vector where a single entry is 1 and all others are 0. However, for high cardinality categorical features containing thousands of unique categories, such as merchant ID or postal zip code, one-hot encoding fails. Creating a one-hot vector with 10,000 dimensions creates massive, sparse input matrices that explode parameter counts and waste GPU memory bandwidth. To handle high cardinality categorical features efficiently, we utilize entity embedding layers. An entity embedding layer maps discrete categorical integer IDs into dense, low-dimensional continuous vector spaces, such as mapping a merchant ID into a 16-dimensional continuous vector. Inside the neural network, the embedding layer is stored as a learnable weight matrix of shape 10,000 rows by 16 columns. When a categorical merchant ID enters the layer, the engine performs a fast array lookup, retrieving the corresponding 16-dimensional row vector. Crucially, the entries inside embedding matrices are not fixed. They are initialized randomly and updated automatically via backpropagation during training alongside all other network weights. During training, the embedding layer learns semantic relationships in space. Merchants with similar transaction patterns and risk profiles are automatically pulled closer together in the 16-dimensional embedding space. Entity embeddings replace sparse, high-dimensional one-hot vectors with compact, information-dense representations, dramatically improving network performance on categorical data. We now enter Phase 3, Network Architecture System Design. Having pre-processed our continuous numerical features and categorical embedding vectors, we design the structural topology of our multitask neural network. At the base of the network stands the input concatenation layer. The input layer takes all standardized continuous feature vectors and all 16-dimensional categorical embedding vectors, and concatenates them horizontally into a single unified input vector of size d. This concatenated input vector feeds directly into the shared representation backbone. to construct a high-capacity, stable backbone capable of learning deep feature hierarchies without suffering from vanishing gradients, we implement a sequence of dense residual blocks. A dense residual block consists of two fully connected linear layers paired with batch normalization, GELU activation functions, and a residual skip connection. Let us trace signal flow through a single dense residual block. Incoming signals pass into the first linear layer, which projects features into a hidden dimension H. The raw linear outputs pass into a batch normalization layer. Batch normalization is a critical architectural component in modern deep networks. It normalizes the pre-activation outputs of a layer across the current mini-batch, subtracting the mini-batch mean and dividing by the mini-batch standard deviation. It then applies two learnable parameters, a scaling parameter gamma and a shifting parameter beta, allowing the network to dynamically learn the optimal scale and mean for each feature. Batch normalization stabilizes the internal covariate shift across deep layers, smoothing the loss landscape and allowing us to train with significantly higher learning rates without risking numerical instability. Following batch normalization, signals pass through a GELU activation function, introducing smooth nonlinear curvature. The signals then pass through the second linear layer and a second batch normalization layer. Before applying the final activation of the residual block, we introduce the residual skip connection. The residual skip connection takes the original incoming input tensor that entered the block and adds it directly, element-wise, to the output tensor produced by the second linear layer. This additive skip connection transforms the block's learning objective. Instead of forcing the linear layers to learn an absolute mapping from scratch, the residual block is forced to learn only a residual modification, the difference or delta between the input and the target mapping. Geometrically, additive residual skip connections create uninterrupted gradient highways through the network computational graph. During backpropagation, error gradients flowing backward encounter the additive skip connection junction. The calculus derivative of an addition operation is exactly 1.0. Consequently, error gradients pass backward through the skip connection completely unattenuated, flowing directly to early layers without decaying, allowing deep backbone networks to train effortlessly. To regularize the shared backbone, we insert an inverted dropout layer with a drop probability of 0.2 between residual blocks, preventing neuron coadaptation. At the top of the shared backbone, the extracted high-dimensional representation vector splits and feeds into three parallel task-specific heads. The fraud detection head consists of a dedicated linear hidden layer of 32 neurons, a GELU activation, and a final linear output layer of one neuron paired with a sigmoid activation function, producing the predicted fraud probability. The risk estimation head consists of a dedicated linear hidden layer of 32 neurons, a GELU activation, and a final linear output layer of one neuron without an activation function, producing the continuous scalar risk score. The risk categorization head consists of a dedicated linear hidden layer of 32 neurons, a GELU activation, and a final linear output layer of C neurons paired with a softmax activation function, producing the categorical probability distribution. We now proceed to Phase 4, Training Infrastructure and Production Pipeline. To train our multitask architecture efficiently, we construct a high-throughput, distributed training loop in PyTorch, incorporating multitask loss weighting, mixed precision acceleration, and distributed data parallelism. First, we define the multitask loss function. Each output head generates its own specific loss penalty. The fraud head computes binary cross-entropy loss, the risk estimation head computes Huber loss, and the categorization head computes categorical cross-entropy loss. The global scalar loss minimized by backpropagation is computed as a weighted linear combination of these three individual task losses. We assign scalar loss weights alpha, beta, and gamma to balance the gradient magnitudes across tasks. If one task's loss generates gradients that are 10 times larger than the others, that task will dominate backbone weight updates, suppressing learning on the remaining tasks. To maintain balanced multitask learning, we utilize automatic uncertainty weighting, allowing the network to dynamically learn the optimal loss weight coefficients during training based on the homoscedastic uncertainty of each task. Second, to accelerate training speed and reduce GPU memory footprint by 50%, we enable automatic mixed precision training. Standard deep learning frameworks perform all computations using single precision 32-bit floating point numbers, known as FP32. However, modern GPU hardware tensor cores feature specialized execution units designed for half-precision 16-bit floating point numbers, known as FP16 or BF16. Automatic mixed precision dynamically executes memory-heavy matrix multiplications and convolutions in 16-bit precision, delivering up to 3 times higher execution throughput while cutting VRAM allocation in half. Simultaneously, it maintains a master copy of parameter weights in 32-bit precision and uses gradient scaling to prevent tiny 16-bit floating point gradients from underflowing to 0 during backpropagation. Third, to scale training across multi-GPU server clusters, we implement distributed data parallelism, abbreviated as DDP. Under distributed data parallelism, the training pipeline spawns an independent worker process for each GPU installed in the server cluster. Each GPU worker process maintains its own identical replica of the complete neural network model and optimizer state in its local VRAM. During every training step, the data loading pipeline partitions the global mini-batch into equal sub-batches and distributes one sub-batch to each GPU worker process. Each GPU independently executes a forward pass across its sub-batch, computes its local task losses, and executes a backward pass to compute local parameter gradients. Before optimizers update parameter weights, the GPU workers execute an all-reduce collective communication operation across the high-speed inter-GPU interconnect bus. The all-reduce operation averages the gradient vectors across all GPUs in real time, ensuring that every GPU worker receives the exact same global average gradient vector. The optimizers on all GPUs then perform synchronized weight update steps, keeping all model replicas in perfect lockstep synchronization without centralized bottleneck servers. We now advance to Phase 5, comprehensive model evaluation and diagnostic auditing. Once training completes, we evaluate our model on the held-out test set. Evaluating a real-world enterprise model using simple classification accuracy is severely misleading, particularly in fraud detection where negative samples outnumber positive fraud events by a ratio of 1,000 to 1. A trivial model predicting non-fraud for every sample achieves 99.9% accuracy while missing 100% of fraud events, resulting in catastrophic business losses. To perform a rigorous diagnostic audit, we evaluate a comprehensive suite of threshold-independent and threshold-dependent metrics. For binary fraud classification, we compute the precision recall curve and the area under the receiver operating characteristic curve, known as ROCAUC. Precision measures the proportion of predicted fraud alerts that were truly fraudulent. True positives divided by the sum of true positives plus false positives. Recall measures the proportion of actual fraudulent events that were successfully caught by the model. True positives divided by the sum of true positives plus false negatives. High recall guarantees that dangerous fraud attacks do not slip through undetected. Because precision and recall exist in constant structural tension, increasing classification sensitivity increases recall but degrades precision. We summarize overall performance by calculating the area under the precision recall curve, known as PRAUC. Unlike ROCAUC, which can appear artificially optimistic on highly imbalanced datasets, PRAUC focuses exclusively on the positive target class, providing an undistorted evaluation of fraud detection capacity. To translate model probability scores into real-time operational decisions, we perform threshold optimization using a business cost matrix. In production, the model outputs a continuous fraud probability between 0 and 1. To trigger an automated transaction block, we must select an operational decision threshold. Defaulting to a threshold of 0.5 is rarely optimal for business goals. Selecting the optimal decision threshold requires balancing the concrete financial cost of a false positive against the cost of a false negative. A false positive occurs when a legitimate customer's transaction is incorrectly flagged as fraud and blocked. The cost of a false positive includes transaction processing fee losses and customer dissatisfaction. A false negative occurs when a true fraud attack slips through undetected. The cost of a false negative is the total dollar value of the stolen transaction plus regulatory penalty fines. We construct a financial cost function that computes the net monetary loss incurred across the validation dataset as a function of the decision threshold. By sweeping the decision threshold from 0.01 to 0.99, we identify the exact threshold coordinate that minimizes net financial cost to the enterprise, deploying that optimized threshold to the production inference engine. Beyond performance metrics, enterprise deployment requires model interpretability auditing to explain model decisions to regulators and auditors. To explain our deep neural networks predictions, we utilize SHAP, short for Shapley Additive Explanations, and integrated gradients. SHAP is grounded in cooperative game theory. It treats each input feature as a player in a game, and the final model prediction as the total payout. SHAP calculates the exact marginal contribution that each feature makes to the difference between the model's baseline average prediction and the specific prediction for a given sample. Integrated gradients computes feature importance by integrating the path gradients of the model's output with respect to the input features along a straight interpolation line running from a neutral baseline input vector to the actual input vector. Generating SHAP values and integrated gradients explanations for flagged transactions provides clear, human-interpretable feature importance scores, such as highlighting that an unusual transaction location and a sudden spike in transaction velocity were the primary drivers for a fraud alert, satisfying regulatory compliance requirements. Finally, we execute Phase 6, deployment, latency optimization, and production operations. Training a model in PyTorch or TensorFlow produces a dynamic Python checkpoint file. However, running a live production microservice that loads a full Python interpreter and framework engine introduces excessive memory overhead and high inference latency, making it impossible to satisfy strict sub-10 millisecond SLA requirements. To prepare our trained multitask model for low-latency production serving, we execute a two-stage export and optimization pipeline, compiling to ONNX and optimizing via TensorRT. First, we export our trained PyTorch model to the Open Neural Network Exchange format, universally known as ONNX. ONNX defines a standardized, framework-agnostic computational graph representation format. Exporting to ONNX traces the computational graph, freezing trained parameter weights into a compact, language-independent binary file. Second, we pass the compiled ONNX model to NVIDIA TensorRT, a specialized high-performance deep learning inference optimizer engine. TensorRT performs aggressive hardware-specific graph optimizations for deployment, fusing adjacent layers, eliminating unused graph branches, selecting optimal CUDA matrix kernels for the specific GPU architecture, and reallocating VRAM memory buffers for batch processing. To achieve maximum inference throughput and minimize memory footprint, we apply post-training INT8 quantization inside TensorRT. Standard trained models store parameter weights as 32-bit floating point numbers. Quantization compresses 32-bit floating point numbers into 8-bit signed integers, known as INT8. 8-bit integer quantization reduces model file size and memory footprint by 75%, compressing a 1 GB model down to 250 MB, and enables the GPU to utilize hyperfast integer tensor math execution units, reducing inference latency by up to 300% while preserving over 99.5% of the original FP32 model accuracy. The optimized TensorRT INT8 engine is deployed inside a dedicated Triton Inference Server container. Triton Inference Server manages dynamic request batching, concurrent model instance execution across GPUs, and health monitoring interfaces, serving real-time prediction requests via gRPC and REST APIs with sub-5 millisecond P99 latency. Once deployed to production, system operations transition to continuous model monitoring and drift detection. A model deployed to production does not operate in a static environment. Real-world data distributions evolve constantly over time due to shifting economic conditions, emerging fraud patterns, and user behavior changes. We monitor two primary operational degradation phenomena: feature drift and concept drift. Feature drift, also known as covariate shift, occurs when the statistical distribution of incoming input features changes over time, even if the relationship between features and target labels remains stable. We monitor feature drift by executing real-time population stability index checks and Kolmogorov-Smirnov statistical tests, comparing incoming production feature distributions against the historical training baseline distribution. Concept drift occurs when the underlying mathematical relationship between input features and target labels changes over time, such as fraudsters inventing an entirely new attack strategy that bypasses historical patterns. We monitor concept drift by continuously tracking real-time prediction accuracy metrics against incoming ground truth feedback labels. When feature drift or concept drift metrics cross designated statistical alert thresholds, our automated operations pipeline triggers an automated retraining workflow, pulling the latest window of production data, executing data preprocessing pipelines, fine-tuning the neural network architecture, running diagnostic verification audits, and staging an updated model for canary deployment. By mastering this complete production lifecycle, from multitask formulation and leakage-free data pipelines, through dense residual architecture design and mixed precision distributed training, to cost-optimized decision thresholds, INT8 quantization, and automated drift monitoring, you possess the full, elite engineering mental model required to build and scale modern deep neural network architectures in industrial environments. To scale modern neural networks beyond single-node constraints into massive distributed clusters processing billions or trillions of parameters, system architects must master advanced model parallelism paradigms and memory optimization engines, specifically tensor parallelism, pipeline parallelism, the zero redundancy optimizer, and low precision numerical formats. When a neural network model's parameter count grows so massive that its weight matrices, optimizer states, and activation tensors exceed the VRAM capacity of a single accelerator GPU, standard data parallelism fails. Data parallelism requires every GPU to store a complete replica of all model parameters and optimizer states. If a model requires 200 gigabytes of VRAM merely to store its weights, a single 80 gigabyte GPU cannot load the model at all. To train models that surpass single GPU VRAM limits, system architects slice the model itself across multiple GPUs using model parallelism. Model parallelism encompasses two primary intranode and internode strategies: tensor parallelism and pipeline parallelism. Tensor parallelism, pioneered by architectures such as Megatron LM, splits individual weight matrices and tensor operations across multiple GPUs operating in parallel within a single layer. Consider a massive dense linear layer whose weight matrix contains 16,000 rows and 16,000 columns. Under column parallel tensor parallelism, the system splits this weight matrix vertically into two equal halves of 16,000 rows by 8,000 columns, placing the first half on GPU 0 and the second half on GPU 1. During the forward pass, the input feature vector is broadcast identically to both GPUs. GPU 0 multiplies the input vector by the first weight half, producing the first half of the output activation vector. Simultaneously, GPU 1 multiplies the input vector by the second weight half, producing the second half of the output vector. The two GPUs then execute an all-gather collective communication operation across high-speed NVLink interconnects, concatenating their partial outputs into the complete output vector. Under row parallel tensor parallelism, the weight matrix is split horizontally across GPUs, and the input vector is partitioned along its feature channels. GPU 0 and GPU 1 compute their partial matrix products independently, and then execute an all-reduce sum operation, adding their outputs element-wise to produce the final layer activation. To scale models across multiple server nodes connected by standard network fabrics, system architects implement pipeline parallelism. Pipeline parallelism partitions a deep neural network sequentially across a chain of GPUs. GPU 0 holds layers 1 through 10, GPU 1 holds layers 11 through 20, GPU 2 holds layers 21 through 30, and GPU 3 holds layers 31 through 40. During execution, data signals flow sequentially from GPU to GPU like a physical conveyor belt. GPU 0 processes layers 1 through 10 and transmits the intermediate activations to GPU 1 over the network fabric. GPU 1 processes layers 11 through 20 and transmits activations to GPU 2, continuing down the pipeline to the final loss node. However, naive pipeline parallelism introduces a severe operational inefficiency known as the pipeline bubble. In a naive pipeline, GPU 1 sits completely idle while GPU 0 is processing the first layer. Similarly, when the backward pass reaches GPU 0, GPUs 1, 2, and 3 sit idle waiting for the next forward step. The idle processor time across the cluster is the pipeline bubble, which can waste up to 50% of compute capacity. To shrink the pipeline bubble and maximize GPU utilization, modern pipeline engines implement microbatching, exemplified by gpipe and interleaved pipeline schedules. Microbatching divides a mini-batch into m smaller microbatches. GPU 0 processes the forward pass for microbatch 1 and immediately transmits its output to GPU 1. While GPU 1 is processing microbatch 1, GPU 0 does not sit idle. It immediately begins processing the forward pass for microbatch 2. By piping multiple microbatches sequentially through the pipeline, all GPUs across the server cluster operate simultaneously in parallel execution, dramatically shrinking the pipeline bubble to a small fraction of total step time and achieving near-linear scaling across hundreds of nodes. Alongside model parallelism, managing memory footprint requires understanding where GPU memory is consumed during training. In deep network training, GPU VRAM consumption is dominated by 4 distinct categories: model parameters, parameter gradients, activation tensors, and optimizer states. Consider a model containing 1 billion parameters trained using single-precision 32-bit floating-point numbers. Storing 1 billion FP32 parameters requires 4 gigabytes of VRAM. Storing their FP32 gradients requires another 4 gigabytes of VRAM. However, the largest memory consumer in modern training is the optimizer state. When using the Atom optimizer with FP32 master weights, Atom maintains a 4-byte master copy of each weight, a 4-byte first moment vector, and a 4-byte second moment vector for every parameter in the network. Consequently, Atom's optimizer state requires 12 bytes of memory per parameter, 3 times larger than the model weights themselves. Storing optimizer states for a 1 billion parameter model consumes 12 gigabytes of VRAM, bringing total static memory overhead to 20 gigabytes before a single activation tensor is allocated. To eliminate memory redundancy without splitting model layers, the Zero Redundancy Optimizer, universally known as Zero, was developed. Zero eliminates memory redundancy across data parallel GPUs by partitioning optimizer states, gradients, and parameters across all available GPUs, while maintaining the functional execution of data parallelism. Zero operates in 3 progressive stages: Stage 1, Stage 2, and Stage 3. Zero Stage 1 partitions the optimizer states across all data parallel GPUs. If training is distributed across 16 GPUs, each GPU stores only 1/16 of the total Atom optimizer state vectors. During parameter updates, each GPU updates only its assigned 1/16 subset of parameters, and then executes an all-gather operation to synchronize the updated parameters across all GPUs. Zero Stage 1 reduces total memory footprint by up to 4 times with 0 additional communication overhead. Zero Stage 2 partitions both the optimizer states and the parameter gradients across the GPUs. Each GPU retains gradient buffers only for its assigned parameter subset. As backward passes complete, gradients are reduced and partitioned directly to their respective owner GPUs using a reduce scatter operation. Zero Stage 2 reduces memory footprint by up to 8 times. Zero Stage 3 partitions all 3 components, optimizer states, parameter gradients, and model parameters across all GPUs. Under Zero Stage 3, no single GPU holds a complete copy of the model parameters. During the forward pass, when a GPU is about to execute a specific layer, it performs a fast on-the-fly all-gather operation to temporarily fetch the required layer parameters from neighboring GPUs, computes the layer activation, and immediately discards the fetched parameters from VRAM before moving to the next layer. During the backward pass, it fetches the parameters on the fly again to compute gradients. Zero Stage 3 reduces memory footprint linearly with the number of GPUs in the cluster. Distributed across 64 GPUs, Zero Stage 3 enables a cluster to train multi-hundred billion parameter models without requiring complex manual layer splitting, democratizing massive deep learning scale. Finally, we examine the frontier of numerical representation, low-precision floating-point formats, specifically bfloat16 and FP8. Standard single-precision floating-point, FP32, uses 1 sign bit, 8 exponent bits, governing dynamic range, and 23 mantissa bits, governing numerical precision. Half-precision floating-point FP16 uses 1 sign bit, 5 exponent bits, and 10 mantissa bits. While FP16 reduces memory footprint by half, its narrow 5-bit exponent gives it a tiny dynamic range, causing small gradients to underflow to 0 and large activations to overflow to infinity, requiring complex loss scaling managers. To solve FP16's dynamic range limitations, Google engineered Brain Floating Point 16, universally known as bfloat16. bfloat16 uses 1 sign bit, 8 exponent bits, matching the exact dynamic range of full FP32, and truncates the mantissa to 7 bits. By preserving FP32's 8-bit exponent, bfloat16 possesses the exact same dynamic range as FP32, completely eliminating gradient underflow and overflow issues without requiring loss scaling managers, while cutting memory footprint and doubling matrix math throughput. For ultra-high throughput deep learning engines, hardware architectures incorporate 8-bit floating-point formats, known as FP8. FP8 introduces 2 complementary format variants tailored for specific computational phases: E4M3 and E5M2. The E4M3 format uses 4 exponent bits and 3 mantissa bits. It provides higher numerical precision at the expense of a narrower dynamic range, making it ideal for forward pass activations and weight matrices where precision is critical. The E5M2 format uses 5 exponent bits and 2 mantissa bits. It provides a wider dynamic range matching FP16 at the expense of lower precision, making it ideal for backward pass error gradients where preserving wide dynamic range is essential to prevent gradient underflow. By executing forward passes in FP8E4M3 and backward passes in FP8E5M2, paired with delayed block scaling factors called microscaling, modern GPU acceleration engines deliver up to 4 times higher matrix execution throughput and 75% memory reduction compared to FP32, enabling the training of frontier neural networks at unprecedented operational efficiency. To complete our foundational exploration of neural network architectures, we must examine how deep learning systems process sequential dependencies and manage high-speed memory bandwidth using memory-efficient attention mechanics, specifically online softmax renormalization and tiled memory access. When a neural network processes sequential or structured data, such as natural language sentences, time series telemetry, or multidimensional feature graphs, the system must capture long-range dependencies between distant elements in the sequence. Historically, sequential modeling relied on recurrent neural networks, or RNNs. Recurrent networks maintain an internal hidden state vector that acts as a sequential memory buffer, updating the hidden state step by step as tokens flow through time. However, recurrent architectures possess 2 severe structural bottlenecks: sequential computation constraints and vanishing temporal memory. Because recurrent networks update their hidden state step by step, computing the activation for step 10 requires waiting for the completion of step 9, which requires step 8, and so forth. Sequential step dependencies prevent hardware parallelization, leaving thousands of GPU parallel cores unutilized during sequence processing. Furthermore, as backpropagation signals travel backward through hundreds of recurrent time steps, Repeated matrix multiplications cause gradients to decay to zero or explode, preventing recurrent networks from capturing long-range dependencies. To eliminate sequential bottlenecks and capture arbitrary long-range dependencies in parallel, modern deep architectures rely on self-attention engines. Self-attention computes pairwise relational scores between every element in a sequence simultaneously in a single parallel operation. Given an input sequence of length n, self-attention projects each input token into three distinct vectors: a query vector, a key vector, and a value vector. To determine how much attention token A should pay to token B, the engine computes the dot product between the query vector of token A and the key vector of token B, divides by the square root of the feature dimension, and applies a softmax function across all sequence tokens. The resulting softmax probabilities represent an attention matrix of shape n by n, which is used to compute a weighted sum of the value vectors. However, computing standard self-attention introduces a severe memory bandwidth bottleneck, the n by n attention matrix. For an input sequence containing 10,000 tokens, storing the full 10,000 by 10,000 floating-point attention matrix in GPU VRAM requires allocating 100 million floating-point values for a single head and single sample. Storing these massive intermediate attention matrices during forward passes consumes gigabytes of VRAM and forces GPU execution units to spend most of their time reading and writing to slow high-bandwidth VRAM memory, a classic memory-bound bottleneck. To break the attention memory bottleneck and allow deep networks to process ultra-long sequences, modern architectures implement flash attention. Flash attention restructures the attention calculation to eliminate the explicit n by n attention matrix allocation in slow VRAM entirely, executing the complete attention pass inside superfast GPU SRAM register memory using SRAM tiling and online softmax renormalization. To understand flash attention intuitively, visualize GPU memory hierarchy as two distinct tiers: a massive but slow high-bandwidth VRAM memory, and a microscopic but insanely fast SRAM register memory located directly on the GPU core. Standard attention loads query, key, and value matrices from VRAM into SRAM, computes the massive n by n attentions, writes the full n by n matrix back out to VRAM, reads it back from VRAM to compute softmax, and writes the softmax result back to VRAM. Reading and writing the massive intermediate matrix to VRAM repeatedly throttles execution speed. Flash attention completely eliminates writing the intermediate attention matrix to VRAM. It divides the query, key, and value matrices into small blocks or tiles that fit perfectly inside fast SRAM register memory. It loads one block of queries and one block of keys into SRAM, computes their local dot products, and evaluates their local softmax values. However, because softmax requires a global normalization denominator computed across the entire sequence, how can flash attention normalize local blocks correctly without seeing the entire sequence at once? Flash attention achieves this using online softmax renormalization. As flash attention iterates block by block through the key and value matrices in SRAM, maintains a running maximum scalar and a running exponential sum accumulator for each query row. When a new block of keys is processed in SRAM, flash attention dynamically rescales the previously accumulated output block using the updated running maximum and sum, merging the new block's contribution seamlessly into the running output accumulator. Once all key and value blocks have been swept through SRAM, the running output accumulator contains the exact mathematically correct attention output vector. Flash attention writes only the final output vector back to VRAM, completely bypassing the allocation of the n by n attention matrix in main memory. By eliminating intermediate VRAM reads and writes, flash attention reduces memory overhead from quadratic order n squared down to linear order n, while increasing execution speed by up to 400%. By synthesizing memory-efficient attention, zero-redundancy parallelism, mixed precision operations, and robust gradient dynamics, modern software engineers possess the full spectrum of tools required to architect, train, and deploy frontier deep neural network systems at scale. Congratulations on completing this masterclass. By taking the time to journey through this entire deep dive, you have built a comprehensive, rock-solid mental model of deep learning, from the fundamental mathematical mechanics of a single neuron to multi-layer feed-forward architectures, backpropagation calculus, loss landscapes, advanced optimizers, regularization strategies, and production-grade system deployment. You now possess the foundational engineering intuition required to design, debug, and scale modern neural network systems with confidence.